December 1972, Gene Cernan stepped off the lunar surface, climbed a ladder, and no human being went back for 52 years. Then in 2026, NASA launched Artemis II, 4 astronauts, the most powerful rocket ever built, and the headline said we'd return to the moon. Except the crew never landed. They flew around it and came home, and if that sounds like a disappointment, this video's going to completely change your mind about why. If you enjoy the video, make sure to hit like and subscribe. Let's begin. NASA named this program Artemis. Artemis is the twin sister of Apollo in Greek mythology. The program is explicitly framed as a return to the moon. The rocket is called the Space Launch System. The capsule is called Orion. Everything about the branding screams we are going back. So when Artemis II launched with 4 humans aboard, Reed Wiseman, Victor Glover, Christina Koch, and Canadian astronaut Jeremy Hansen, every major news outlet ran some variation of the phrase moon mission. What they buried in paragraph 7, if they mentioned it at all, was a single critical phrase: free return trajectory. That phrase changes everything. A free return trajectory means the spacecraft uses the moon's gravity to slingshot itself back to Earth without ever entering lunar orbit, without descending toward the surface, and without any possibility of landing. It's a flyby. A controlled, deliberate, scientifically essential flyby. But a flyby nonetheless. The crew came within approximately 7,400 kilometers of the lunar surface. That's roughly the distance from New York to London. Close enough to see extraordinary detail, not close enough to touch. To understand why Artemis II didn't land, you have to understand the architecture NASA designed years before a single bolt was tightened on Orion. The Artemis program was never a single mission. It was always a 3-phase escalation, each phase proving technology and validating systems before the next phase could attempt something harder. Artemis I, launched November 2022, was an uncrewed test flight. No humans. The goal was simple and brutal in its engineering demands. Prove that the SLS rocket can reach the moon's vicinity, prove that Orion's heat shield can survive re-entry at 11.1 kilometers per second, approximately 40,000 kilometers per hour, or 24,850 miles per hour, nearly 36 times the speed of sound, and prove the spacecraft can be recovered from the ocean intact. Orion travelled 1.3 million kilometers over 25.5 days and survived re-entry temperatures of approximately 2,760 degrees Celsius. The heat shield worked. The mission was declared a success. Artemis II was always designed as the crude version of that same basic test. Not a landing attempt. A crude validation that human beings can survive the radiation environment beyond low Earth orbit, that the life support systems function across the full mission duration, that crew vehicle communication works at lunar distances, and that Orion's navigation handles human occupants as variables. 4 humans on a path that took them around the moon and back. That was the entire plan. Artemis III, originally targeted for no earlier than 2026, though schedules have already shifted repeatedly, is the landing mission. And even that mission is contingent on a separate vehicle entirely. The SpaceX Starship human landing system, which has to independently prove it can autonomously land on the moon, refuel in lunar orbit, and ascend back to rendezvous with Orion. Artemis II not landing wasn't a compromise. It was the architecture operating exactly as designed. Let's put Artemis II's actual trajectory in perspective, because the numbers are genuinely staggering even without a landing. The mission placed 4 humans farther from Earth than any humans had travelled since Apollo 17 in December 1972, a gap of more than 5 decades. At its farthest point, Orion reached approximately 9,000 kilometers beyond the moon's far side, placing the crew about 370,000 kilometers from Earth at the closest lunar approach, and up to 379,000 kilometers at the trajectory's deepest point. For context, the International Space Station orbits at roughly 408 kilometers altitude. Artemis II flew more than 900 times farther from Earth than the ISS. That number should hit you. 900 times farther. The free return trajectory itself is an elegant piece of orbital mechanics. The spacecraft requires no engine burn to return to Earth. The moon's gravity does the work. This is not laziness. It's the safest possible architecture for a first crewed flight, because if every single engine on Orion fails after the lunar flyby, the crew still comes home. Apollo 13 famously used this principle in 1970 after an oxygen tank explosion crippled the service module. The crew survived because the trajectory itself was their emergency exit. Artemis II was built with that same philosophy as a deliberate non-negotiable design requirement. One of the primary scientific objectives of Artemis II, one that the landing narrative completely overshadowed, was measuring the radiation environment that the crew experienced beyond Earth's magnetosphere. This is not a footnote. It may be the most medically critical data collected by the mission. Earth's magnetosphere deflects the majority of cosmic rays and solar energetic particles. The ISS, orbiting inside that shield at 408 kilometers altitude, exposes astronauts to roughly 1 millisievert per day, about the equivalent of 20 chest X-rays. The moment you leave low Earth orbit, that number changes dramatically. During Artemis I's 25-day uncrewed mission, sensors aboard Orion, including the Matryoshka Astrorad radiation experiment, which used 2 human-shaped phantom torsos filled with radiation detectors, recorded total doses in the range of 2.7 to 3.0 millisieverts for a simulated crew member behind the capsule's shielding. That's over the full mission. During a solar particle event, doses can spike by a factor of 100 or more in hours. NASA's current career radiation limit for astronauts is 600 millisieverts, a limit designed to keep the increased lifetime cancer risk below 3%. A round trip to Mars would expose a crew to an estimated 300 to 900 millisieverts, depending on solar activity. Artemis II's crude radiation measurements gave NASA real biological response data, not mannequin approximations. That data directly feeds into the shielding design for the Orion spacecraft that will eventually carry humans to Mars. The flyby, medically speaking, may be worth more than a landing. Here's the physics that the press releases never explain. In space, everything is measured in delta V, the change in velocity required to move from one trajectory to another. Delta V is your currency. You spend it with rocket fuel, and you can never get it back for free. Getting from Earth's surface to low Earth orbit costs approximately 9,400 meters per second of delta V. Getting from low Earth orbit to a trajectory toward the Moon costs another 3,100 meters per second. So far, that's what Artemis II did, plus the lunar flyby itself. Here's where landing explodes the budget. To enter lunar orbit from the flyby trajectory costs approximately 900 meters per second. To then descend from lunar orbit to the surface costs another 1,900 meters per second, and to ascend from the surface back to lunar orbit costs another 1,900 meters per second. Then you need another 900 meters per second to escape lunar orbit and return to Earth. The total additional delta V to land and return versus simply flying by is approximately 5,600 meters per second, more than half the cost of getting from Earth's surface to orbit in the first place. You effectively need a second moon mission's worth of propulsion budget on top of everything you've already burned, just to go from flyby to landing. That is the physical reason Artemis II didn't land, not budget, physics. Apollo 17 touched down on the Taurus Littrow Valley on December 11th, 1972. Gene Cernan was the last human to stand on the lunar surface. He said, "We leave as we came, and God willing, as we shall return with peace and hope for all mankind." Then he climbed the ladder. And for 52 years, no human being went back. That gap is almost incomprehensible in the context of technological progress. In 1972, the most powerful computer on Earth had less processing power than the phone in your pocket. Today, a smartphone has roughly 100,000 times the processing power of the Apollo guidance computer. We mapped the human genome, we built the internet, we discovered thousands of exoplanets, and yet, No human being left low Earth orbit between December 1972 and the Artemis program. 52 years. That's not a pause, that's a generational erasure of capability. Artemis II's crewed flyby broke that drought. It re-established in living human bodies with real-time telemetry what it actually takes to send people to lunar distances. The data gaps created by a 52-year hiatus are not trivial. Human physiology research in deep space is essentially starting over. Artemis II wasn't a compromise. It was the first step in rebuilding an institutional capability that the human species allowed to atrophy for half a century. Forget everything you think you know about spacecraft design. The Orion multi-purpose crew vehicle is not an upgraded Apollo capsule. It is not the space shuttle with better marketing. It is a fundamentally different machine, designed for a fundamentally different threat environment. And understanding why it was built the way it was built explains exactly why Artemis II had to happen before Artemis III could even be attempted. When the space shuttle returned from the ISS, it was travelling at roughly 7.8 kilometers per second. Orion, returning from the Moon, arrives at Earth's atmosphere at approximately 11.1 kilometers per second, about 40,000 kilometers per hour, or nearly 25,000 miles per hour. That's faster than a rifle bullet by a factor of more than 10. In terms of kinetic energy, the difference between 7.8 and 11.1 kilometers per second is not a 42% increase in heat load. Kinetic energy scales with the square of velocity. Orion re-enters with roughly 2.1 times the kinetic energy of a shuttle re-entry. That energy has to go somewhere. Almost all of it becomes heat. The Orion heat shield is the largest of its kind ever built, 5 meters in diameter, compared to Apollo's 3.9 meters. It uses Avcoat ablator material, a substance that literally chars and burns away in a controlled fashion, carrying heat energy away from the spacecraft in the process. During Artemis I's re-entry, surface temperatures on the heat shield reached approximately 2,760 degrees Celsius. That's hotter than the surface of most stars you can see with the naked eye. It's nearly half the surface temperature of the Sun. Artemis II's crewed re-entry gave NASA something Artemis I could not: real-time human physiological data during the most violent deceleration phase of the mission. Peak deceleration during re-entry runs approximately 4 to 6 Gs, 4 to 6 times the force of gravity. For an 80-kilogram person, that means experiencing an effective body weight of 320 to 480 kilograms. A person of that weight in those conditions is not fully conscious, cannot operate controls normally, and relies entirely on automated systems. Validating that those automated systems work with a living crew aboard was non-negotiable before any landing attempt. Artemis II's Orion didn't just fall straight into the atmosphere. It performed what's called a skip re-entry, a maneuver so precise and so geometrically demanding that it would have been impossible to execute reliably in the Apollo era. Here's how it works. Orion enters the upper atmosphere at a shallow angle, decelerates partially, then skips back out of the atmosphere like a stone skipping across water. Except it's doing this at 11 kilometers per second with 4 humans inside. After the skip, it re-enters the atmosphere a second time at a steeper angle for final deceleration and parachute deployment. The purpose: landing accuracy. A straight ballistic re-entry from lunar velocity would create a landing footprint thousands of kilometers wide, essentially impossible to predict or control. The skip re-entry allows Orion to target a splashdown zone precise to within approximately 10 kilometers. The computational requirements alone are staggering. The trajectory must be calculated based on atmospheric density models, real-time spacecraft velocity, entry angle, within a window of approximately 5.5 degrees, because too shallow and you skip off permanently into space, and too steep and the heat shield is overwhelmed, and current solar activity affecting upper atmosphere density. All of this must be computed and adjusted in real time during a phase of flight lasting approximately 20 minutes, during which communications with ground control are intermittent due to the plasma sheath surrounding the vehicle. Artemis I proved the physics. Artemis II proved it works with human beings aboard who are generating unpredictable biological heat, carbon dioxide, and mass distribution changes in real time. The ISS life support system is a marvel of engineering, but it's also backed up by a 408-kilometer delivery radius. If something goes wrong, a Soyuz capsule can have a crew on the ground in 3.5 hours. At lunar distance, there is no rescue, there is no resupply, there is no help. Every consumable on board is everything you get. Orion's environmental control and life support system must maintain cabin pressure at approximately 101.3 kilopascals, oxygen concentration between 19.5 and 23.5%, carbon dioxide partial pressure below 0.57 kilopascals. To prevent hypercapnia, the CO2 poisoning that causes headaches, confusion, and eventually death, and cabin temperature between 18.3 and 26.7 degrees Celsius. It must do this continuously without resupply for the full mission duration. Water is carried in fixed supply. Artemis II's free return trajectory lasted approximately 10 days. Each crew member requires a minimum of 2 litres of potable water per day. Total minimum water requirement for 4 crew over 10 days, 80 litres. Food is pre-packaged. Waste is managed by a system that has to function in microgravity without venting anything to the exterior during radiation-sensitive mission phases. Every gram of every consumable is accounted for before launch, with zero margin for error. Orion's structure is not a single hull. It's a layered radiation mitigation system built into the vehicle's architecture in ways that aren't obvious from the outside. The aluminum structure provides some shielding. Water storage tanks are positioned strategically around the crew compartment. Water is an excellent radiation absorber because of its high hydrogen content, and hydrogen nuclei are particularly effective at scattering high-energy protons. Polyethylene components serve a similar function. But here's what the shielding cannot do. It cannot stop galactic cosmic rays. Galactic cosmic rays are high-energy atomic nuclei, primarily protons and helium nuclei, travelling at relativistic speeds from outside the solar system. They carry so much energy that they pass through centimetres of aluminum as though it doesn't exist. The only effective shield against galactic cosmic rays is mass, specifically meters of water or polyethylene, which Orion cannot carry. A vehicle that could fully shield against galactic cosmic rays would be too heavy to launch. During Artemis II's transit phases, crew members were exposed to galactic cosmic ray flux of approximately 1 to 2 millisieverts per day during solar minimum conditions, roughly the equivalent of a full-body CT scan every 24 hours. The mission's 10-day duration kept total crew dose within acceptable limits. A 6-month lunar surface stay would require either surface habitat shielding using regolith as a radiation buffer or dedicated storm shelters. Artemis II's radiation measurements, taken with biological bodies in the actual environment, give NASA the ground truth needed to design those systems. Orion sits atop one of the most powerful escape systems ever built, the launch abort system. In the event of a catastrophic failure during launch, or the first 100 seconds of flight, the most dangerous phase, the launch abort system fires its abort motor, which produces approximately 400,000 pounds of thrust for approximately 2 seconds. The result: the crew capsule is pulled away from the rocket at an acceleration of approximately 17 Gs, 17 times the force of gravity, reaching a safe altitude in under 3 seconds. For context, 17 Gs applied to a human body for even a fraction of a second will cause vision tunnel, loss of fine motor control, and potential loss of consciousness. Fighter pilots black out at sustained 9 Gs. The Orion launch abort system is not designed for comfort. It's designed to get 4 people away from an exploding rocket fast enough to survive. The logic behind Artemis II's sequence is brutally simple, but it's the logic that drove the entire Artemis architecture. You cannot ask 4 human beings to ride a vehicle to the lunar surface and back on its first crewed flight. The risk profile is unacceptable under any rational engineering framework. Every system that failed quietly on an uncrewed vehicle kills someone on a crewed one. During Artemis I, NASA identified 13 technical anomalies requiring investigation after the mission. issues with the heat shield ablator performing differently than predicted, concerns about European service module thrusters, and data inconsistencies in the power systems. None of these caused mission failure. All of them required engineering review and corrective action before a crewed mission flew. Artemis II as the first crewed flight then identified its own set of system behaviours that only emerge when living humans are producing heat, moisture, carbon dioxide, and physical movement inside the vehicle. Those findings feed directly into the Artemis III configuration. The sequence isn't bureaucratic caution. It's the difference between a program that lands humans safely and a program that kills them. The Space Launch System is the most powerful rocket ever to successfully launch. Not the most efficient, not the cheapest, the most powerful in terms of raw thrust at liftoff, and understanding why that power is necessary, what it costs to generate it, and why no alternative exists, yet explains why Artemis II required this specific machine, and why NASA cannot simply swap to something cheaper for the next mission. At liftoff, the SLS Block 1 generates approximately 39.1 million newtons of thrust, 8.8 million pounds force. The Saturn V, the rocket that took Apollo astronauts to the moon, generated approximately 35.1 million newtons. The SLS is more powerful than the Saturn V. That sentence should stop you cold because the Saturn V was considered the engineering pinnacle of the 20th century, the machine that defined what human ambition could build in a decade, and the SLS beats it. That thrust comes from a combination of 4 RS-25 engines, originally used on the space shuttle, burning liquid hydrogen and liquid oxygen in the core stage, plus 2 5-segment solid rocket boosters. The boosters alone produce approximately 75% of the total liftoff thrust. They burn a solid propellant mixture at a rate that cannot be throttled or shut down once ignited. Each booster contains approximately 629,000 kilograms of propellant. They burn for approximately 126 seconds before separation. The SLS Block 1 can deliver approximately 95,000 kilograms to low Earth orbit, or approximately 27,000 kilograms to a translunar injection trajectory. For comparison, a SpaceX Falcon 9 lifts approximately 22,800 kilograms to low Earth orbit. The SLS lifts 4 times that. But here's the catch. The Falcon 9 costs approximately $67 million per launch. The SLS costs approximately $4.1 billion per launch. You could buy 61 Falcon 9 launches for the price of one SLS flight. The reason the SLS has to be this powerful comes down to a fundamental constraint of physics. To send a heavy crewed spacecraft to the moon in a single launch, you need to accelerate it to approximately 10.8 kilometers per second translunar injection velocity. Everything below that and your spacecraft falls back toward Earth. Everything above that and you overshoot the moon. Orion, with its European service module, has a launch mass of approximately 26,500 kilograms. To push that mass from low Earth orbit to translunar injection requires a delta V of approximately 3,100 meters per second. The propellant required to produce that delta V is roughly 3 times the mass of the payload itself at the point of the burn. The interim cryogenic propulsion stage, the upper stage of the SLS that performs the translunar injection burn, carries approximately 27,200 kilograms of liquid hydrogen and liquid oxygen to do this job. No currently operational rocket other than the SLS can perform this entire sequence in a single launch with a crew capsule of Orion's size. SpaceX's Starship Super Heavy system, still in testing as of Artemis II's flight, theoretically exceeds the SLS in payload capacity, but theoretically and in testing are not the same as certified for crewed deep space missions. The SLS exists because it's the only currently operational system that can do this job today with humans aboard. The 4S-25 engines on the SLS core stage are not new engines. They are former Space Shuttle main engines, some of the most flight-proven rocket engines in history, with over 1 million seconds of total test and flight time accumulated across the shuttle program's 135 missions from 1981 to 2011. NASA had 16 of these engines in storage after shuttle retirement. The SLS program refurbished them for reuse in Artemis I and II. Here's where it gets complicated. The shuttle's RS-25 engines were reusable. They were recovered from each mission, inspected, refurbished and reflown. The SLS drops its core stage and all 4 RS-25 engines into the ocean after every launch. They burn at approximately 1,860 degrees Celsius, produce approximately 222,000 newtons of thrust each at sea level, and are then lost forever. After the stockpile of shuttle-era engines is exhausted, NASA will switch to a new production S-25 engine for later Artemis missions, at a unit cost of approximately $146 million per engine, 4 per launch, $584 million in engines per flight that are thrown away. This is not an engineering choice, it's an architectural consequence. The SLS was designed around existing shuttle infrastructure to save development time and money, a decision that made the rocket operational sooner but locked in expendability as a permanent feature. The SLS's 5-segment solid rocket boosters are direct descendants of the 4-segment boosters used on the Space Shuttle, but larger, carrying 20% more propellant. Each booster is approximately 54 meters tall and weighs approximately 726,000 kilograms at launch. They are the largest solid rocket boosters ever flown. Solid rocket motors, once ignited, cannot be shut down. This is a fundamental chemistry constraint. The oxidizer and fuel are mixed together in the solid grain, and combustion continues until the propellant is exhausted. There is no throttle valve. There is no emergency stop. This is why the Space Shuttle Challenger disaster was unsurvivable. The solid boosters could not be shut off after the O-ring failure allowed a flame jet to breach the external tank. The SLS mitigates this risk through the launch abort system. If the vehicle starts to break apart, the system yanks the crew capsule away before the booster's energy is released uncontrollably. But there is no abort that saves the vehicle itself. Once you light the solid rocket boosters, you are committed. To assemble the SLS and Orion stack, NASA uses the Vehicle Assembly Building at Kennedy Space Center, a structure so large that clouds form inside it. The Vehicle Assembly Building is 160 meters tall, 218 meters long, and 158 meters wide. It covers 8 acres and encloses 3.66 million cubic meters of space. It was originally built for Saturn V assembly in the 1960s and modified for the Space Shuttle. For the SLS, it required further modification and new platforms, new lifting equipment, and structural reinforcements to handle the SLS's different mass distribution compared to the shuttle stack. The SLS and Orion, once assembled, stand approximately 98 meters tall on their mobile launcher platform. The stack is transported from the Vehicle Assembly Building to Launch Complex 39B on the Crawler Transporter 2, a machine weighing approximately 2.7 million kilograms, capable of carrying loads up to 8.2 million kilograms, moving at a maximum speed of approximately 1.6 kilometers per hour. The 6.7 kilometer journey from the building to the pad takes approximately 10 to 12 hours. SpaceX's Starship is designed to eventually lift approximately 100,000 to 150,000 kilograms to low Earth orbit in its fully reusable configuration. That's over twice the Celeste Block 1 payload to low Earth orbit. And because it's fully reusable, per launch cost could theoretically drop below $10 million with sufficient flight cadence, a factor of 400 cheaper than the SLS. This comparison is why NASA's own architecture for Artemis III depends on Starship as the human landing system, an implicit acknowledgement that the SLS cannot economically serve as the sole heavy lift vehicle for a sustained lunar program. But Starship's development timeline has slipped repeatedly. As of Artemis II's flight, Starship had not yet achieved the orbital refueling demonstration required to qualify it for the lunar lander role. The SLS exists not because it's the best solution, but because it's the ready solution. And in human spaceflight, ready now beats theoretically better later when 4 lives are in the equation. People assume landing on the moon is simple compared to landing on Mars. No atmosphere, so no atmospheric drag to fight, no weather, no wind. just a dead rock you can settle gently onto. Every single one of those assumptions is dangerously wrong. The moon's lack of atmosphere is not a simplification. It's one of the most brutal engineering constraints in space exploration, and it's a primary reason why Artemis III's landing is vastly more complex than Artemis II's flyby. On Mars, an incoming spacecraft can use the thin atmosphere, surface pressure approximately 610 pascals, about 0.6% of Earth's sea level pressure, to aerobrake. The spacecraft deploys a heat shield, the atmosphere slows it from orbital velocity, and parachutes or retro rockets handle the final deceleration. It's not easy, but the atmosphere does real work. The Mars Science Laboratory slowed from 5.8 km per second to approximately 0.75 km per second using atmospheric drag alone before its sky crane deployed. The Moon has no atmosphere. Zero. Atmospheric pressure on the lunar surface is approximately 10 to the power of negative 10 torr, 10 times lower than the best vacuum achievable in most Earth laboratories. There is no aerobraking, there is no parachute. Every single meter per second of orbital velocity, approximately 1,680 meters per second for a low lunar orbit at 100 kilometers altitude, must be removed by the rocket thrust. Entirely. You land by pointing engines at the ground and burning until velocity reaches zero at the exact moment altitude reaches zero. The precision required is measured in fractions of a second and fractions of a meter per second. Apollo's lunar module descent engine burned for approximately 12 minutes during powered descent, consuming approximately 8,200 kilograms of propellant. The descent stage alone, which stayed on the surface, weighed approximately 10,334 kilograms fully fueled. That's just the landing vehicle, not the crew capsule, not the service module, just the lander. Apollo landed near the lunar equator, where solar power is consistent and terrain is relatively flat. Artemis III is targeting the lunar south pole, specifically areas near permanently shadowed regions such as those near Shackleton Crater, Gay-Gerlach Crater, and the connecting ridge between them. This is not a random choice. It's a scientific and resource decision that dramatically complicates the landing. The lunar south pole's permanently shadowed regions have never seen direct sunlight in potentially billions of years. Temperatures in these regions reach approximately negative 230 degrees Celsius, colder than the surface of Pluto. But NASA's LCROSS mission in 2009 deliberately impacted one of these shadows and confirmed the presence of water ice, approximately 5.6% water by mass in the debris plume. The Lunar Reconnaissance Orbiter has since mapped substantial water ice deposits across multiple permanently shadowed regions, with estimates of hundreds of millions to potentially over 1 billion metric tons of ice total. Water ice is everything for a sustained lunar presence. Electrolyze it and you get oxygen to breathe and hydrogen to burn as rocket fuel. The South Pole is where the ice is, but landing there requires navigating terrain that is permanently dark in some areas, deeply cratered, and covered in slopes that challenge any landing system. The Artemis III landing system, the SpaceX Starship human landing system, must autonomously navigate this terrain without GPS, without a communication satellite network in polar lunar orbit, and without any prior surface infrastructure. Artemis II's free return trajectory did not approach the South Pole at close range. But the mission's data on navigation precision, communication reliability, and system performance all directly feed into the South Pole landing attempt. The Moon's surface is covered in regolith, a layer of fragmented rock and dust produced by billions of years of meteorite impacts, ranging from boulders to particles smaller than 1 micrometer. This material is not like Earth's sand. Earth's sand has been rounded by water erosion over millions of years. Lunar regolith has never touched water. Every particle is jagged, angular, and abrasive at the microscopic level. Astronaut Harrison Schmitt during Apollo 17 noted that lunar dust penetrated every seal, jammed every joint, and coated every surface it touched within hours of surface operations. The particle size distribution of lunar regolith peaks at approximately 40 to 130 micrometers, fine enough to be inhaled deeply into lung tissue. On Earth, particles of that size are absorbed and cleared by respiratory mucus systems. On the Moon, in a spacesuit environment, lunar dust particles that breach suit seals through abrasion at joints, through outgassing events, through dust tracked into habitats on boots, pose a real inhalation hazard. Apollo astronauts reported symptoms consistent with lunar dust exposure: sneezing, watery eyes, and throat irritation after every EVA. For short Apollo stays of 1 to 3 days on the surface, this was manageable. For the planned 30-day Artemis surface stays, it becomes a medical engineering problem requiring active mitigation. Additionally, regolith is electrostatically charged by the solar wind and UV radiation, causing it to cling to surfaces with remarkable adhesion. Solar panels coated in regolith lose efficiency rapidly, optical sensors blur, mechanical joints seize. The entire surface operation plan for Artemis III must account for a material that is simultaneously sharp, adhesive, fine enough to be airborne, and ubiquitous. The Moon's rotation period is approximately 29.5 Earth days, the same as its orbital period around Earth, which is why we always see the same face. This synchronous rotation means the lunar day and night are each approximately 14.75 Earth days long. During the lunar day, surface temperatures on equatorial regions reach approximately plus 127 degrees Celsius. During the lunar night, they plunge to approximately negative 173 degrees Celsius. That's a temperature swing of 300 degrees Celsius across a 2-week cycle. At the South Pole, the geometry changes significantly. Because of the Moon's nearly zero axial tilt, the Sun sits perpetually near the horizon at the poles. Peaks of eternal light, elevated crater rims and ridges near the South Pole receive nearly constant sunlight, making them ideal for solar power generation. The Malapert Massif, approximately 122 kilometers from the South Pole, is lit approximately 94% of the time. These peaks are essentially the only viable power generation sites for a sustained South Pole outpost. Earth's atmosphere burns up approximately 100 tons of meteoritic material per day before it reaches the surface. The Moon has no such protection. Every meteorite, from kilometer-scale impactors to micrometer-scale dust particles travelling at 10 to 72 kilometers per second, reaches the surface directly. A micrometeorite 1 millimeter in diameter travelling at 20 kilometers per second carries kinetic energy equivalent to a rifle bullet. A spacesuit punctured by such an impact at an exposed joint would depressurize in seconds. The Apollo-era suits were rated for a working life of approximately 115 hours of EVA, short enough that cumulative micrometeorite damage was manageable. Artemis surface suits must be rated for multiple 8-hour EVA sessions over 30 days, 240 hours of potential exposure, across missions that will likely recur annually. The suit architecture for Artemis III must balance micrometeorite resistance against flexibility and thermal regulation. It's an engineering contradiction with no clean resolution, only managed compromise. On Earth, sunlight scatters through the atmosphere, illuminating shadows. Even in deep shadow, you can see reasonably well because light bounces off every surface in every direction. The Moon has no atmosphere. Sunlight doesn't scatter. Shadows on the Moon are absolute, not dim, not dusky, but completely, totally black. The transition from full sunlight to shadow is instantaneous and complete. Near the South Pole, this creates extreme terrain challenges. A crater rim in full sunlight can be photographed at extraordinary detail. The crater floor 10 meters below may be in a permanent shadow so complete that optical cameras see literally nothing without artificial illumination. Navigating terrain in these conditions requires either powerful artificial lighting, LiDAR systems, or radar, all of which consume power and add mass. The Artemis III Starship must autonomously identify a safe landing zone in terrain that may be partially or heavily shadowed during the approach phase. Autonomous landing sensors must discriminate between shadow and crater in real time, at descent velocities of approximately 1 to 3 meters per second during the final approach phase. Getting this wrong by a margin of meters means landing on a slope, tipping, and losing the vehicle and crew. There is no go-around at zero velocity, zero altitude on a world with no atmosphere. Artemis II flew without Gateway, but Gateway is the reason Artemis II won't be the template for every future mission. The Lunar Gateway, NASA's planned lunar orbit space station, is simultaneously one of the most ambitious infrastructure projects in human history and one of the most controversial engineering decisions NASA has ever made. Understanding what it is, what it does, and why it matters explains the entire logic of why the Artemis program is structured the way it is. The International Space Station orbits Earth at approximately 408 kilometers altitude in a nearly circular low Earth orbit. It's visited regularly. It has a crew of 7 people. Supply ships arrive every few months. Gateway is nothing like this. Gateway is designed to orbit the Moon in a near-rectilinear halo orbit, a highly elliptical, 3-dimensional orbit that takes the station as close as approximately 1,500 kilometers from the lunar surface at its closest approach, and as far as approximately 70,000 kilometers at its farthest. One complete orbit takes approximately 6.5 days. This orbit is not circular, not equatorial, and not intuitive. It's a Lagrange point adjacent trajectory that balances gravitational influences from both Earth and Moon to remain stable with minimal propulsion expenditure. Why this specific orbit? Because it provides near continuous communication with Earth, relatively stable solar power availability, and access to landing trajectories for virtually any point on the lunar surface, including the South Pole, without requiring prohibitive propulsion burns to change orbital inclination. A station in standard low lunar orbit would have to burn significant fuel to reach south polar landing trajectories. In the near-rectilinear halo orbit, the geometry is fundamentally more favourable for south pole access. Gateway's power and propulsion element is not a traditional chemical rocket spacecraft. It uses solar electric propulsion, converting sunlight to electricity via large solar arrays, and using that electricity to ionize and accelerate xenon gas through ion thrusters. Ion thrusters produce very low thrust, on the order of 0.1 to 0.9 newtons per thruster, compared to chemical rockets producing thousands or millions of newtons, but they have extraordinarily high efficiency, specific impulse of approximately 3,000 seconds compared to approximately 450 seconds for the best liquid hydrogen and liquid oxygen chemical engines. This means ion thrusters use approximately 6.7 times less propellant per unit of velocity change than chemical rockets. The power and propulsion element uses this efficiency to maintain Gateway's orbit indefinitely, make orbital adjustments, and serve as the primary propulsion module for the entire Gateway station. Without Gateway, a crew going from Earth to the lunar surface requires a single stack. S launches Orion. Orion goes to the Moon. A separate lander meets Orion in lunar orbit. Crew transfers to the lander, lands, ascends, transfers back to Orion, goes home. This is essentially the Apollo architecture. It works, but it requires launching everything on a single trajectory window, coordinating perfect simultaneous arrival of multiple vehicles, and accepting that any single system failure ends the mission. With Gateway, the architecture becomes modular. The Starship human landing system can be launched separately, months in advance, and parked at Gateway waiting for the crew. If the lander needs a repair or inspection, it can be done at Gateway before the crew commits to the lunar surface. If a crew mission slips by weeks, the lander waits. This is the fundamental architectural advantage of Gateway. It decouples the crew transport mission from the lander logistics mission. The SLS plus Orion handles crew. Commercial vehicles handle logistics. Gateway connects them. Without Gateway, every mission requires perfect simultaneous coordination of every element on a single timeline. With Gateway, the elements are buffered, or you have a place to store things, wait, repair, and coordinate without the crew sitting in their capsule counting consumables. Gateway is not a NASA-only project, it is a multi-agency international program. ESA is contributing the Esprit module and the IHAB habitation module. JAXA is contributing components of the IHAB module. Canada is contributing an advanced robotics system, the Canadarm3, which will be more autonomous than ISS's Canadarm2, capable of operating without constant human control. The international partnership structure creates both advantages and constraints. Funding is diversified. Technology contributions leverage each partner's engineering strengths. Commitments from allied nations create programmatic stability. Canada's Canadarm3 contribution specifically is why a Canadian astronaut, Jeremy Hansen, flew on Artemis II. The CSA's participation in Gateway robotic systems was formalised with an agreement that reserved a seat on an early Artemis crewed mission for a Canadian astronaut. Hansen's presence aboard Artemis II was simultaneously a scientific and diplomatic milestone. Every data point from Artemis II feeds directly into Gateway's human factors design. The life support system performance, the crew physiological data, the radiation measurements, the communication protocol performance at lunar distances, all of it informs how Gateway's interior is configured for human occupation. Specifically, the carbon dioxide removal data from Artemis II's life support system tells Gateway engineers what the real-world CO2 generation rate from 4 crew members in microgravity during a range of activity levels actually is, with real human subjects in the real radiation and thermal environment of deep space. Simulation and ground-based testing give you models. Artemis II gives you ground truth. The difference between a model and the reality in life support system design can be the difference between a crew that stays healthy and a crew that faces a CO2 emergency on day 14 of a 30-day Gateway stay. You've heard about astronaut health risks on the ISS, bone density loss, muscle atrophy, vision changes. Those are real, and they happen in low Earth orbit inside Earth's magnetosphere, with regular resupply with emergency evacuation options, with Earth just 408 kilometers below. Now multiply every one of those risks by the fact that you're 370,000 kilometers from the nearest hospital, surrounded by cosmic radiation with no magnetic shield, consuming fixed supplies with zero resupply possible, and facing an 11 km per second re-entry as your only way home. The human body was not designed for this, and Artemis II was, at its core, a physiological experiment. Astronauts on the ISS lose approximately 1 to 2% of bone density per month in weight-bearing bones, hips, spine, lower limbs. This happens because microgravity removes the mechanical loading that stimulates bone remodeling on Earth. Osteoblasts, bone-building cells, reduce activity. Osteoclasts, bone-resorbing cells, continue. The net result is progressive skeletal weakening at a rate that mirrors severe osteoporosis in postmenopausal women. On ISS, this is mitigated through approximately 2.5 hours of daily resistive exercise. Even with this regimen, bone density losses of approximately 0.9% per month in the hip and 0.6% per month in the spine are typical. After a 6-month ISS mission, recovery of lost bone density takes approximately 2 to 3 years. After a 12-month mission, complete recovery has not been consistently demonstrated. One of the most unexpected discoveries of long-duration spaceflight has been spaceflight-associated neuroocular syndrome. In microgravity, body fluids shift headward toward the upper body and head because gravity no longer pulls fluid in the lower body. This shift increases intracranial pressure, which in turn presses on the optic nerves and reshapes the eyeball. Approximately 70% of long-duration ESAS astronauts develop measurable vision changes. Some develop permanent vision loss. The mechanism is still not fully understood. Intracranial pressure measurements from astronauts on ISS show elevated pressure during microgravity exposure, with values occasionally exceeding 25 millimeters of mercury. The threshold for clinical concern in patients on Earth is approximately 20 millimeters of mercury. For a 10-day Artemis II mission, syndrome progression would be limited. The ISS data shows measurable changes occurring predominantly after 30 or more days, but Artemis II measured baseline indicators and tracked the fluid shift dynamics specific to the Orion capsule environment. Galactic cosmic rays don't just increase cancer risk, They interact with neural tissue in ways that may directly impair cognition. High-charge, high-energy cosmic ray nuclei, primarily ion nuclei moving at relativistic speeds, can traverse neurons in a straight line, depositing ionizing energy along a track through the cell. Unlike X-rays or gamma radiation, which spread energy diffusely, these particles create a dense ionization track, a literal line of molecular damage through whatever tissue they pass through. NASA-funded research using animal models has demonstrated measurable cognitive impairments following high-energy radiation exposure equivalent to a Mars mission duration. Artemis II crew members wore personal dosimeters continuously throughout the mission. Blood draws before and after the mission allowed measurement of radiation biomarkers, proteins that mark double-strand DNA, breaks in cells, telomere length changes, and cytokine levels indicative of inflammatory response to ionizing radiation. These biomarkers, measured in real human beings who experience the actual deep space radiation environment, give NASA data that no Earth-based accelerator simulation or computational model can fully replicate. The human circadian rhythm, the approximately 24-hour internal clock governing sleep, cortisol levels, immune function, and dozens of other physiological processes, is synchronized primarily by light exposure. On the ISS, astronauts experience approximately 16 sunrises per day, requiring artificial light management to maintain circadian alignment. On Artemis II, the lighting environment is different again. During the translunar coast phases, solar illumination is constant and unvarying. There is no orbital sunrise, there is no day-night cycle. Sleep quality in microgravity is documented as significantly worse than on Earth. ISS astronauts report an average of approximately 6 hours of sleep per night, compared to a recommended 8 hours, despite scheduled 8.5-hour sleep periods. The causes include noise levels, elevated carbon dioxide levels, and psychological stress of the mission environment. Sleep deprivation accumulates. A crew member consistently getting 6 hours instead of 8 shows measurable cognitive impairment equivalent to full sleep deprivation after approximately 2 weeks, impairments in reaction time, decision-making, and risk assessment. For a mission that requires precise navigation decisions, emergency response capability, and complex system management, sleep quality is not a comfort concern. It's a safety-critical performance variable. Artemis II's sleep monitoring data, wrist-worn motion sensors tracking sleep stages, cognitive performance tests administered during flight, and cortisol level measurements provided the first real-world characterization of sleep quality in Orion's specific environment. Spaceflight suppresses immune function. This is well documented from ISS data. Latent herpes viruses reactivate in approximately 47% of short-duration and 89% of long-duration astronauts, detectable in saliva and urine samples throughout missions. On Earth, these viruses are kept suppressed by a healthy immune system. In spaceflight, psychological stress, disrupted sleep, radiation exposure, and altered microbiome composition combine to weaken immune surveillance. The implications for a lunar mission are serious. An astronaut who develops a viral reactivation syndrome or bacterial infection on the lunar surface faces treatment options limited to whatever medication was packed before launch. There are no pharmacies on the moon. Drug efficacy and stability change in the radiation environment. NASA studies have shown that medications stored in space show accelerated degradation relative to Earth storage controls, with some drugs showing potency reductions of 30 to 40% after 3 to 6 months of spaceflight storage. The Orion capsule's pressurized crew volume is approximately 8.95 cubic meters, habitable volume of roughly 9 cubic meters for 4 people. For comparison, a standard American parking space is approximately 14.9 square meters in area. 4 people for 10 days in a space smaller than a parking space exposed to radiation, dependent on machines for every breath, with Earth growing visibly smaller outside the windows. Psychological stress in isolated, confined environments is a primary mission risk for long-duration spaceflight. The Mars 500 simulation, a ground-based study that isolated 6 crew members for 520 days in a simulated spacecraft environment, found that subjects showed increasing sedentariness, disrupted sleep, and, in some cases, clinical depression by the mission's midpoint, even without actual radiation or physiological spaceflight stressors. Artemis II's 10-day duration provided a compressed but real test of how behavioural health protocols function in the actual mission environment, with data feeding directly into the longer duration mission designs to come. You pull out your phone, you call someone in Tokyo, the call connects in under a second. You assume that because we have satellites and fibre optics and 5G towers covering most of the inhabited Earth, communicating with a spacecraft 370,000 kilometres away is a solved problem. It isn't. The physics of deep space communication imposes constraints that no amount of technology can fully overcome, and those constraints had direct implications for Artemis II's mission design and will determine what Artemis III can and cannot do on the lunar surface. Light and radio waves, which travel at the speed of light, covers approximately 300,000 kilometers per second. The Moon is approximately 384,400 kilometers from Earth on average. The one-way signal travel time to the Moon is therefore approximately 1.28 seconds. Round-trip communications delay approximately 2.56 seconds. That 2.56 second delay sounds trivial. In normal conversation it's merely noticeable. But consider its implications for mission operations. If a crew member reports an emergency and waits for a response from Mission Control, 2.56 seconds elapse before Mission Control even hears the report. Ground controllers formulate a response. That response travels another 1.28 seconds. By the time the crew receives guidance, a minimum of 5 to 10 seconds have passed. In a rapidly evolving emergency, a fire, a pressure leak, a medical crisis, 10 seconds is a very long time. This is why Artemis missions require crew autonomy in ways that ISS operations do not. On ISS, Mission Control in Houston can and does provide real-time guidance for virtually every anomaly. The latency of ISS communications is negligible. At lunar distances, Mission Control is a slow response resource, not a real-time partner. Artemis II trained its crew extensively in autonomous decision-making protocols, the ability to diagnose, decide, and act without waiting for ground guidance, specifically because the communications physics make ground-dependent operations dangerous. NASA's Deep Space Network is the ground-based antenna system that communicates with all of NASA's deep space assets, from lunar missions to the Voyager probes, now over 23 billion kilometers from Earth. The Deep Space Network consists of 3 antenna complexes positioned approximately 120 degrees apart in longitude: Goldstone in California's Mojave Desert, Madrid in Spain, and Canberra in Australia. This positioning ensures that at least one complex has line of sight to any point in the deep space sky as Earth rotates. The largest antennas are 70-meter diameter dishes capable of receiving signals at extraordinarily low power levels. Voyager 1's transmitter broadcasts at 22 watts, roughly the power of an energy-efficient light bulb. The 70-meter dishes can detect that signal despite the power having spread across a sphere 470 billion kilometers in diameter during transit. For Artemis II, Deep Space Network communication operated at approximately 80 to 100 megabits per second during peak communications windows, supporting high-definition video, continuous telemetry, voice communications, and scientific data downlinks simultaneously. Orion's skip reentry creates a communications blackout. When the spacecraft enters the upper atmosphere at 11 kilometers per second, atmospheric friction ionizes the air around the capsule into a plasma sheath, a layer of charged particles that absorbs and reflects radio waves. During this phase, approximately 4 to 6 minutes of total communications blackout occurs. 4 to 6 minutes doesn't sound long, but those are 4 to 6 minutes during which the crew is experiencing peak deceleration, peak heating, maximum g-forces, and is making real-time adjustments to the re-entry trajectory based on guidance computer outputs. If something goes wrong during blackout, if the heat shield behaves unexpectedly, if parachute deployment fails, if the skip trajectory deviates, mission control learns about it after the fact. Either Orion emerges from blackout intact, or it doesn't. There is no intervention possible. The lunar south pole creates a geometry problem that Artemis II's trajectory didn't face, but Artemis III will. From Earth, you can communicate with any point on the lunar near side because it's directly visible. The South Pole, sitting at the Moon's geometric edge from Earth's perspective, spends significant fractions of the lunar month in positions where the lunar terrain itself blocks line of sight to Earth. A crew on the surface near Shackleton Crater at the South Pole can communicate directly with Earth only when the geometry is favourable, estimated at approximately 70 to 80% of the time for the highest elevation landing sites, dropping significantly in lower terrain. For the remaining 20 to 30% of mission time, communication requires relay. As of Artemis II's flight, this relay constellation was not yet in place. A solution partially in place is not the same as a solution fully in place. Artemis III's crew cannot operate on the lunar surface safely without a communications infrastructure that provides near-continuous contact with Earth. GPS is a constellation of 31 operational satellites in medium Earth orbit. GPS signals degrade at distances beyond approximately 50,000 kilometers from Earth. At lunar distance, GPS does not work. There are no equivalent positioning satellites around the Moon. Artemis II navigated entirely by inertial navigation, star trackers, and range and rate tracking from Deep Space Network ground stations using Doppler shifts in the communication signal to precisely measure velocity and range. The resulting position knowledge for Orion during Artemis II was accurate to approximately 1 kilometer in position and less than 0.1 meters per second in velocity. Impressive for a spacecraft 370,000 kilometers from Earth, but requiring continuous ground tracking to maintain. For Artemis III's landing phase, navigation must be even more precise. The Starship must autonomously determine its exact position relative to the target landing zone, autonomously identify terrain hazards, and autonomously execute a powered descent to a surface touchdown with positional accuracy of approximately 10 meters, without GPS, without a pre-mapped landing pad, and without real-time ground guidance during the final descent phase where the 1.28 second communication delay makes ground commanding impossible. Artemis III's lunar landing does not depend solely on NASA's hardware. It depends on a SpaceX vehicle, the Starship Human Landing System, that was still undergoing test flights as Artemis II flew. This is the elephant in the room that defines the entire Artemis landing timeline. The SLS launches Orion. Orion carries the crew. But the thing that actually touches the Moon is built by a private company, uses a propellant combination never before used for a crewed landing, and requires an orbital refueling operation that has never been demonstrated with humans depending on it. The Apollo lunar module was a purpose-built vehicle, 2 stages, specifically designed for lunar landing and ascent, carrying 2 people for 1 to 3 days on the surface. It weighed approximately 14,696 kilograms fully fueled at landing. It was optimized at every design point for its single mission. The SpaceX Starship Human Landing System is a variant of SpaceX's Orbital Starship vehicle repurposed for lunar landing. The variant is approximately 50 meters tall. It uses liquid methane and liquid oxygen propellants, a combination that offers higher specific impulse than Apollo's hypergolic propellants and the theoretical ability to manufacture methane on Mars. Starship's Raptor engines burn liquid methane at chamber pressures exceeding 30 megapascals, the highest combustion chamber pressure of any rocket engine ever flown. This high pressure enables high efficiency and thrust density, but also creates extreme engineering challenges in combustion stability, turbopump design, and engine life. The Starship Human Landing System cannot reach the Moon from Earth in a single launch. The vehicle is too massive and requires too much propellant to carry enough fuel for Earth ascent, lunar transit, lunar landing, lunar ascent and return, all in one tank. The solution? Orbital refueling. multiple tanker Starship vehicles launch from Earth, each carrying propellant rather than cargo. They rendezvous with the landing vehicle in Earth orbit or lunar orbit and transfer propellant through cryogenic fluid transfer connections. The propellant, liquid methane at -162 degrees Celsius and liquid oxygen at -183 degrees Celsius, must be transferred in microgravity without significant boil-off losses, without propellant settling issues caused by microgravity, and without cryogenic fluid hammer caused by rapidly stopping fluid flow in cryogenic lines. None of this has ever been done operationally in space with cryogenic propellants at the scale required. The number of tanker flights required to fully fuel a Starship for a lunar mission has been estimated at between 8 and 16 flights, each requiring successful rendezvous, docking and propellant transfer. Methane offers real advantages over Apollo's hypergolic propellants. Methane and liquid oxygen produce a cleaner combustion. No toxic exhaust products at the landing zone, important because lunar surface contamination from propellant exhaust can corrupt science instruments. Methane is non-toxic to handle, unlike hydrazine-based hypergolics. But methane at the lunar South Pole faces specific challenges. Methane freezes at -182 degrees Celsius at atmospheric pressure, which is warmer than the -230 degrees found in permanently shadowed regions. During a surface stay, some methane and liquid oxygen will evaporate through tank vent systems throughout the mission. The propellant loaded at Earth orbit refueling must account for boil-off losses across the entire mission duration, including the surface stay period, or the vehicle will not have sufficient propellant for ascent. The Starship uses vacuum-optimized Raptor engines for the landing burn. The vehicle descends from lunar orbit in a powered trajectory that must slow from approximately 1,680 meters per second lunar orbital velocity at 100 kilometers altitude to 0 at 0 altitude. The burn duration is substantial, potentially 10 to 15 minutes. During this burn, the vehicle is actively gimbaling engines to maintain attitude control, processing terrain relative navigation data from landing sensors, and making autonomous decisions about abort or landing site deviation in real time. The vehicle's sheer size creates additional challenges. A 50-meter tall Starship landing at a South Pole site near Shackleton Crater, which has slopes of up to 30 degrees on its inner crater walls, must assess terrain slope with precision before touchdown. A landing on a slope exceeding approximately 2 to 3 degrees will cause Starship to tip, a catastrophic failure mode that cannot be corrected once it begins. The Artemis II mission profile requires the crew to transfer from the Orion capsule to the Starship while both vehicles are docked at Gateway in the near rectilinear halo orbit. The crew must traverse a pressurized tunnel from Gateway to the Starship cabin, suited for the transfer in case of rapid depressurization. The Starship cabin is located at the top of the vehicle. The crew must then ride an elevator or internal transfer system 50 meters down from the docking port to the main habitation deck, then eventually to the landing level as the vehicle descends. This internal crew transfer system, essentially an elevator operating in microgravity, then in the Moon's 1/6 gravity field, is a unique engineering challenge with no direct spaceflight precedent. NASA originally awarded the Human Landing System contract solely to SpaceX in 2021 at $2.89 billion. Blue Origin, whose proposal was not selected, protested. The Government Accountability Office rejected the protest, but Congress subsequently directed NASA to fund a second competitor. In May 2023, NASA awarded Blue Origin a $3.4 billion contract for a sustainable lunar lander, essentially a second option for missions from Artemis V onward. Blue Origin's Blue Moon lander uses liquid hydrogen and liquid oxygen, the highest specific impulse chemical propellant combination, capable of approximately 450 seconds of specific impulse. The existence of two competing options changes the long-term economics and resilience of the lunar landing program. If Starship encounters a development delay, Blue Moon provides a path forward. If Blue Moon's development slips, Starship maintains continuity. But for Artemis III specifically, the first landing, It's the SpaceX Starship that has to work, and whether it's ready is the central open question of the entire program. The Moon's south pole is not just a science objective, it's a resource deposit that, if accessible, changes the fundamental economics of human spaceflight more than any technology development since the invention of cryogenic propellants. The water ice confirmed in permanently shadowed regions of the lunar south pole is potentially the most valuable substance in the inner solar system, not because of its rarity, but because of where it is and what it enables. The first strong evidence of lunar South Pole water came from the Clementine spacecraft in 1994, which detected a radar signature from permanently shadowed regions consistent with ice. Lunar Prospector in 1998 carried a neutron spectrometer that detected enhanced hydrogen concentrations near both poles, consistent with water ice deposits at concentrations of approximately 1 to 2% by mass in the top meter of regolith. The definitive confirmation came from the L-Cross mission in October 2009. A Centaur rocket stage was deliberately crashed into Cabus crater at approximately 2.5 kilometers per second, vaporizing approximately 150 to 350 tons of regolith and creating a debris plume that was analysed by a following spacecraft and multiple observatories. The spectroscopic analysis identified water vapour, water ice, and numerous other volatiles: methanol, ammonia, hydrogen sulfide, sulfur dioxide, and carbon dioxide. Water was present at approximately 5.6% by mass in the shadowed regolith, substantially higher than earlier estimates. Current estimates of accessible water ice at the lunar South Pole range widely, from approximately 100 million metric tons to over 1 billion metric tons. To put those numbers in perspective, 1 million metric tons of water is approximately 1 billion litres. The lower estimate, 100 million metric tons, is 100 billion litres of water. That sounds modest until you remember that this water is on the Moon, where the cost to deliver water from Earth runs approximately $1 million per kilogram. At that price, 1 metric ton of in situ lunar water is worth $1 billion in launch cost savings. Water can be split into hydrogen and oxygen through electrolysis, passing an electric current through water to break the molecular bonds. At Gateway or on the lunar surface with nuclear or solar power, electrolysis of lunar water ice could produce liquid hydrogen and liquid oxygen, the highest performance chemical rocket propellant combination in situ. A lunar in situ resource utilization propellant plant processing 1,000 kilograms of water per day could produce approximately 111 kilograms of hydrogen and 889 kilograms of oxygen daily. A lunar lander returning to lunar orbit from the surface requires approximately 4,000 to 6,000 kilograms of propellant for the ascent burn. At 1,000 kilograms per day water processing, you could produce enough ascent propellant for one lander per week. The implications are staggering. If lunar water ice can be extracted and electrolyzed at scale, the Moon becomes a propellant depot, a refueling station at the top of Earth's gravity well from which missions to Mars, the asteroids, and the outer solar system can depart without carrying all their propellant from Earth. Every kilogram of propellant not launched from Earth's surface saves approximately $1 to $2 million in launch costs. A single Mars mission requires on the order of 100,000 to 500,000 kilograms of propellant, depending on architecture. Lunar propellant production could reduce Mars mission costs by hundreds of billions of dollars. Beyond propellant, water electrolysis produces oxygen, the oxygen that astronauts breathe. But lunar regolith itself is approximately 45% oxygen by mass, found in mineral oxides such as ilmenite. Hydrogen reduction of ilmenite, passing hydrogen gas over heated ilmenite, produces water vapor and free iron. The water vapor is electrolyzed for oxygen. ESA's European Space Resources Innovation Centre and multiple academic groups have demonstrated this process in laboratory settings. A future lunar base extracting oxygen from regolith and water ice simultaneously would have the potential to become entirely self-sustaining in breathable oxygen, eliminating one of the most massive consumable requirements for long-duration surface habitation. Water isn't the only valuable substance in the permanently shadowed regions. The L-Cross plume analysis identified numerous other volatile compounds that have accumulated over billions of years. Methanol was detected at approximately 1% of the water abundance. Ammonia at approximately 6%. Hydrogen sulfide at approximately 4%. Carbon dioxide at approximately 15%. These compounds represent a chemical library of potential feedstocks for manufacturing, fertilizer production, and chemical synthesis. Carbon compounds are particularly significant. Carbon is one of the elements most difficult to source on the Moon from silicate rocks. Permanently shadowed region carbon compounds could theoretically supply a lunar manufacturing industry with carbon feedstock for polymer production and graphite applications. Here's an irony built into Artemis II that doesn't get enough attention. The landing mission to investigate the South Pole ice could damage the very resource it's trying to study. A rocket engine landing near a permanently shadowed region deposits combustion exhaust, water vapor, carbon dioxide, carbon monoxide directly onto a pristine cold trap surface. Water vapor from the landing engine exhaust will freeze on any surface colder than approximately -60 degrees Celsius, and permanently shadowed region surfaces at -230 degrees Celsius will capture every molecule of landing exhaust with near 100% efficiency. At the South Pole, the contamination would be permanent, frozen into the permanently shadowed region regolith and indistinguishable from primordial ice in subsequent measurements. A poorly planned landing could compromise the scientific value of the ice deposit being investigated for thousands of years. The Artemis III landing zones are being selected with contamination standoff distances in mind. The lander should touch down far enough from the primary ice investigation targets that exhaust plume deposition is minimized. Quantifying exactly how much contamination is produced at what standoff distance is an ongoing modelling effort being validated against test data from engine test firings. It's one of several scientific constraints that directly influence where Artemis III can land. People love to say we went to the Moon in 1969 with less computing power than a modern toaster. The implication is that going back should be trivial. It's not. It's in some ways harder. Not because the physics have changed, the Moon hasn't moved, gravity hasn't shifted, orbital mechanics is the same as it was in 1969, but because the institutions, the engineering culture, the supply chains, the trained workforce, and the accumulated operational knowledge that made Apollo possible were dismantled deliberately, completely, and over decades. And rebuilding them from scratch in the 21st century is a fundamentally different problem than building them the first time. At its peak in 1966, the Apollo program employed approximately 400,000 people across NASA and its contractor network. NASA's budget in 1966 was approximately $5.9 billion, approximately 4.4% of the entire US federal budget. In 2024 dollars, that's roughly $56 billion for a single year. NASA's entire 2024 budget was approximately $25.4 billion, covering the ISS, Artemis, science missions, aeronautics, and everything else NASA does. Apollo at peak cost more in real terms than NASA's entire present budget, and it was focused on a single goal. The Apollo 11 lunar module alone required approximately 5,000 engineering changes between its first design review and the mission flight configuration. The Saturn V required developing 13 separate rocket engines of different types. The manufacturing tolerances achieved in the 1960s without computer-aided design, without CNC machining, and without modern materials science were the product of an industrial workforce with skills that simply no longer exist at the same scale. The F1 engine, the Saturn V's first-stage engine, generating approximately 6.7 million newtons of thrust each, was developed using engineering and test methods that have never been fully reverse-engineered. When NASA attempted an F1 derivative for the SLS in the early 2000s, engineers found that the original engine's combustion stability relied on design features whose precise physical mechanism was not fully documented. The engineers who built it were retired or deceased. Their institutional knowledge did not survive them. The youngest engineers who worked on Apollo as full professionals in 1969 were in their mid-20s. They would be in their late 70s or early 80s today. The engineers who held senior positions in 1969, who made the critical design decisions, who developed the mission rules, who understood the vehicle at the deepest level, are predominantly deceased. The institutional knowledge that made Apollo function in real time, under pressure, in the ambiguous conditions of actual flight, that knowledge is substantially gone. What replaces it is documentation, written records, test data, design drawings, and procedures. Documentation is invaluable, but documentation cannot answer questions that weren't anticipated when the documents were written. It cannot explain why a particular design choice was made in a way that helps a 2020s engineer evaluate whether that choice is still valid with different materials and different manufacturing tolerances. The Apollo program required components manufactured by hundreds of specialized suppliers. When the program ended, those suppliers had no market for their products. They retooled. They went out of business. They merged with larger companies and lost their specialized capabilities. Modern SLS and Orion development encountered this concretely. Orion's heat shield originally used a specific formulation of Avcoat ablator manufactured in a specific way. When production of that formulation was attempted for Artemis, the original manufacturing process produced materials with different thermal properties than the 1960s era product. The exact formula existed, but the specific clay and process inputs had changed subtly due to 50 years of materials industry evolution. The result was that Orion's heat shield performed differently than pre-Artemis models predicted, not catastrophically, but measurably, and in ways that required post-Artemis I engineering review. The supply chain memory had degraded even when the formal recipe was preserved. Apollo's guidance computer operated on 4 kilobytes of RAM and 72 kilobytes of read-only memory. Modern Orion flight software contains approximately 1.2 million lines of code, compared to the Apollo guidance computer's approximately 4,000 lines of assembly. More lines of code means more potential failure modes, more interactions between subsystems, more testing required to validate behavior across all possible conditions. Validating 1.2 million lines of flight-critical software to the required reliability standard, where software failure probability must be less than approximately 1 in a million per flight hour, requires test infrastructure, methodologies, and time that did not exist in Apollo's era. Additionally, cybersecurity, not a concern for 1960s spacecraft, is now a genuine risk vector. A modern spacecraft with complex flight software, communications interfaces, and digital ground support connections exists in a threat environment that Apollo never faced. Apollo 1 killed Gus Grissom, Ed White, and Roger Chaffee in a launchpad fire on January 27, 1967. Apollo 13 barely survived a service module oxygen tank explosion in April 1970. But the Apollo program, operating under Cold War pressure and with a culture that accepted higher risk, pressed forward. The Space Shuttle Challenger disaster in January 1986, killing all 7 crew members, killed 73 seconds after launch due to an O-ring failure that engineers had flagged as a concern the night before. The Columbia disaster in February 2003, killing all 7 crew members on reentry, resulted from foam insulation damage during launch that was known during the mission but not acted on. After Columbia, NASA underwent a complete cultural transformation around safety culture, risk communication, and dissenting opinion. The result is a program that is dramatically safer in process, but dramatically slower in execution. Artemis program safety requirements add approximately 2 to 3 years to every major milestone compared to what an Apollo PACE program would attempt. This is not bureaucratic inefficiency. It's the institutional response to twice losing 7 people due to known risks that were not acted on. Apollo did not have the computational power, the sensor technology, or the communication bandwidth to validate its systems in real time during flight the way Artemis does. Apollo's astronauts were, in important ways, test pilots flying vehicles whose behavior was only partially understood in advance. They improvised, adapted, and accepted unknowns as the cost of operating at the frontier. Artemis II flew with sensor suites that monitored thousands of data streams simultaneously in real time. Vehicle structural loads, heat shield temperature gradients, power system performance curves, crew physiological readings, environmental system outputs, at a level of granularity Apollo never approached. The data density from a single Artemis II mission exceeds the entire Apollo program's cumulative instrumentation output. Every anomaly in that data stream becomes an engineering action item before the next mission. What Artemis II proves, beyond any individual system test, is that the architecture works, the team works, and the data pipeline from vehicle to engineering team to design modification works. Apollo had to trust its engineering. Artemis II verified it. The Artemis program costs a lot of money. Exactly how much is contested, distributed across multiple budget lines, and deliberately obfuscated by accounting conventions that make direct comparison difficult. But the numbers that are documentable are staggering, and understanding them is essential to understanding why the program is structured the way it is, why commercial partnerships are not optional, and why the economics of going back to the moon look radically different from the economics of going there the first time. The total cost of developing the SLS from its inception in 2011 through Artemis II is approximately $23.8 billion for SLS development and approximately $9.4 billion for Orion development, a combined development total of approximately $33.2 billion. Add ground systems modernization of approximately $2.4 billion and mission operations costs, and the total NASA investment from 2011 through Artemis II's flight is approximately $40 to $45 billion. The per-flight cost of the SLS, not including amortized development costs, just the direct launch costs, is approximately $4.1 billion per mission. By comparison, a Falcon Heavy launch costs approximately $150 million. A Falcon 9 costs approximately $67 million. The SLS costs 27 times more per launch than a Falcon Heavy. The NASA Inspector General has repeatedly highlighted this cost structure as unsustainable for a sustained lunar program. While SLS and Orion carry the humans, NASA's Commercial Lunar Payload Services program is attempting to do for lunar cargo delivery what Commercial Crew did for ISS cargo: create a competitive market of private landers that drives down costs through competition. Intuitive Machines' IM-1 mission, the Nova Sea lander, delivered NASA science instruments to the South Polar region in February 2024, landing approximately 300 meters from its intended target before tipping on its side due to a landing leg failure. Despite the anomaly, several instruments returned science data, the first American lunar soft landing since Apollo 17 in 1972. The IM-1 mission cost approximately $118 million, orders of magnitude less than any Apollo-era cargo delivery would have cost. The Commercial Lunar Payload Services model explicitly accepts some failure rate as part of the cost structure. Multiple vendors, each at relatively low contract values, creates a portfolio where some missions fail but the program continues. Astrobotic's Peregrine Mission 1, launched January 2024, suffered a propellant leak shortly after launch and never reached the moon, burning up in Earth's atmosphere. The failure cost approximately $108 million. This is fundamentally different from the zero failure tolerance model that makes SLS so expensive. NASA is not bearing the full cost of the Artemis program alone. ESA's contributions to the program, thus, the European Service Module for Orion, the Esprit and IHAB Gateway modules, and other contributions represent substantial in-kind cost sharing. The ESM contribution alone saves NASA approximately $1 to $1.5 billion in procurement costs per Orion mission. The Artemis Accords, a framework for international cooperation in space exploration signed by 43 nations as of early 2026, create a legal framework for this cost sharing that didn't exist during Apollo. The financial model of Artemis is therefore fundamentally different from Apollo's. It's a distributed, international, public-private partnership model rather than a single government crash program. This makes it more financially resilient to any single government's budget fluctuations. A US budget crisis doesn't automatically cancel ESA's module contributions, but also more complex to coordinate and slower to execute when international partners have different schedule pressures. NASA's total 2024 budget was approximately $25.4 billion. Artemis-related activities consumed approximately $7.5 to $8 billion of that total, roughly 30% of the entire NASA budget. The remaining 70% funds the ISS, science missions including the James Webb Space Telescope and Mars rovers, planetary science, heliophysics, astrophysics, aeronautics research, technology development, and agency operations. This budget competition creates real trade-offs. The cost of 2 SLS flights could fund the entire planetary science division for approximately 2 years. Every dollar spent on Artemis ground systems is a dollar not spent on a planetary science flagship mission. These trade-offs don't have clean right answers. Human exploration and robotic science serve different purposes, but they create pressure on the Artemis program that pure engineering decisions don't. The financial case for lunar return goes beyond the science and exploration objectives. The Moon's permanently shadowed region water ice, if extractable at scale, represents propellant economics that could generate positive return on investment, literally. If a lunar propellant depot could sell rocket-grade liquid oxygen at even 1% of the cost per kilogram versus Earth-launched propellant, the market value of accessible lunar water ice is in the trillions of dollars. Helium-3, a rare isotope of helium deposited in the lunar regolith by solar wind over billions of years, has been proposed as a potential fuel for nuclear fusion reactors. The energy content of 1 kilogram of helium-3 in a fusion reaction is approximately 19 megawatt years, the equivalent of burning approximately 40,000 tons of coal. Total estimated helium-3 inventory in the lunar regolith, approximately 1 million metric tons. Of future fusion energy values, even a fraction of this inventory would represent energy wealth comparable to Earth's entire fossil fuel reserves. These are long-duration economic arguments. Fusion power is not operationally deployed, and lunar mining at industrial scale is decades away at minimum. But they are not science fiction. They are engineering and economic challenges with known physical constraints, and the gap between decades away and happening now closes only if programs like Artemis establish the surface presence and operational experience from which lunar resource utilization can develop. Space programs don't exist in a vacuum. They are funded by governments, shaped by elections, influenced by international competition, and subject to the same pressures as any large public institution. The Artemis program, symbolism, and specifically the decision to fly Artemis II as a crewed flyby rather than a crewed landing, is inseparable from a context that includes a resurgent Chinese space program, a Russian partnership gone cold, budget pressures, and an industry landscape transformed by private companies whose founders have personal stakes in the outcome. China's space program has undergone a transformation in the past decade that the Western press has dramatically underreported. The China National Space Administration and the China Manned Space Agency have executed a methodical, well-funded lunar exploration program that parallels Artemis in objectives and exceeds it in some areas of recent execution speed. Chang'e 5, launched November 2020, successfully returned 1.731 kilograms of lunar samples from the Mons-Rumker volcanic plain in December 2020, making China only the third nation to return lunar samples and the first to do so since Lunar 24 in 1976. Chang'e 6, launched May 2024, successfully returned approximately 1.9 kilograms of samples from the lunar farside South Pole Aitken basin, a feat never previously accomplished. The South Pole Aitken Basin may contain mantle material excavated by the largest confirmed impact event in the inner solar system. scientifically invaluable samples that no program had previously retrieved. China's stated goals include a crewed lunar landing by approximately 2030, the establishment of a lunar research station at the South Pole in the 2030s, and a permanent crewed lunar base by the 2040s. The International Lunar Research Station, a Chinese-Russian project, has signed agreements with multiple nations including Pakistan, the UAE, Azerbaijan, Belarus, South Africa, and others, establishing a rival international coalition to the Artemis Accords framework. The Moon is becoming a venue for competition, with the South Pole's water ice as the strategic resource at the centre of that competition. Whether the US or China establishes the first operational South Pole surface infrastructure will influence who controls access to propellant and resources for decades. Russia's Roscosmos was a potential Artemis Gateway partner in early discussions that broke down irreparably following Russia's invasion of Ukraine in February 2022, and the subsequent cascade of sanctions, export controls, and diplomatic deteriorations. The consequences for Artemis were significant but manageable. The broader decoupling of US-Russia space cooperation has affected ISS operations. Russia has stated intentions to withdraw from ISS by 2028, which would significantly complicate station operations given that Russian segment systems control ISS reboost and certain propulsion functions. The Russian partnership with China on the International Lunar Research Station has accelerated Chinese lunar ambitions by providing Russian technical expertise, particularly in nuclear space power systems, where Russia has substantial heritage, in exchange for Chinese financial and launch resources. The US-Russia space partnership that characterized the post-Cold War era from 1994 through 2021 is effectively over. The new space competition paradigm, US and allies versus China and Russia, is the context within which every Artemis mission will be judged by policymakers and the public. The Apollo program worked with large aerospace contractors, Boeing, North American Aviation, Grumman, McDonnell, Douglas, in cost-plus contracts where the government bore financial risk and the contractors built to specification. The Artemis program adds a fundamentally different category of partner: commercial space companies operating on fixed-price contracts with company money at risk. SpaceX's Human Landing System contract at $2.89 billion fixed price is the largest example, but the Commercial Lunar Payload Services Program, Commercial Crew Transport, and Commercial Satellite Communications for Lunar Relay are all structured to transfer financial risk to commercial entities. When Astrobotic's Peregrine Mission 1 failed, Astrobotic bore the primary financial consequences, not NASA. But this risk transfer means the program's success is now partially dependent on companies whose financial health, management quality, and technical capability are not fully within NASA's control. Boeing's Starliner capsule, NASA's second commercial crew vehicle, intended to provide ISS crew transport backup to SpaceX Dragon, experienced helium leaks and thruster failures during its June 2024 crewed test flight, resulting in the two-person test crew being stranded at the ISS for 8 months and returned by SpaceX Dragon in March 2025. The Starliner situation illustrated the risk of commercial partner technical problems cascading into human spaceflight safety concerns, and the importance of having backup options when a commercial partner encounters difficulties. Artemis II's successful crewed flight to lunar distance achieved something beyond engineering validation. It demonstrated to allies, competitors, and domestic audiences that the program is real, functional, and capable of executing what it promises. The 4 crew members of Artemis II, 2 Americans, 1 Canadian, and in the diverse representation of the crew's racial, gender, and national backgrounds, embodied the Artemis program's explicit commitment to sending the first woman and first person of color to the Moon. Christina Koch, if she flies Artemis III as planned, would be the first woman to land on the Moon. Victor Glover would be the first black astronaut to fly to lunar distance. These symbolic dimensions are deliberately woven into the program's structure. They broaden the coalition of public and congressional supporters in ways that a program representing only the demographic makeup of the Apollo astronaut corps would not. This is not cynical. It's the recognition that space programs are ultimately funded by democratic societies, and democratic societies support things they see themselves in. Artemis II was the second step in a program designed to stretch across decades. To understand why the flyby matters, you have to understand what comes after it, and why each subsequent step is more technically demanding, more scientifically significant, and more consequential for the long-term future of human spaceflight than the one before. Artemis III, currently targeted for no earlier than 2027, though the timeline depends heavily on Starship certification, will be the first crewed lunar landing since Apollo 17 in December 1972. The mission profile is substantially more complex than Artemis II. Orion launches on SLS with 4 crew members. The crew travels to Gateway in the near-rectilinear halo orbit. At Gateway, 2 crew members transfer to the waiting Starship for the lunar surface journey, while 2 remain aboard Gateway. The surface crew lands at a South Pole site, currently one of 13 candidate landing regions identified by NASA, all within 6 degrees latitude of the South Pole. Surface operations are planned for approximately 6.5 days and approximately 4 EVAs. The crew ascends from the surface, rendezvouses with Gateway, transfers back to Orion, and returns to Earth. The scientific objectives include the collection of surface samples from the South Polar region, potentially including ice-bearing regolith, deployment of surface science instruments for long-duration measurement, and the first direct geological survey of a region never visited by Apollo. The ancient, heavily cratered terrain of the South Polar Highlands contains some of the oldest rock on the Moon. Samples from this region could answer fundamental questions about the late heavy bombardment, a hypothesized period approximately 4 billion years ago, when the inner solar system experienced a dramatic spike in impact events, possibly triggered by the orbital migration of the giant planets. Artemis IV, targeted for the late 2020s, will be the first SLS mission to deliver crew directly to Gateway rather than to the lunar surface. The primary objective is assembly of Gateway's habitation module and logistics replenishment of the station. Artemis IV establishes Gateway as an operational outpost rather than a construction project. Artemis V and subsequent missions shift the architecture toward increasing surface stay duration, from Artemis III's 6.5-day initial stay toward the 30-day stays planned for later missions, and eventually toward the 90-day and permanent presence scenarios envisioned for a sustained South Polar base. The human landing system for Artemis V will be Blue Origin's Blue Moon lander if its development proceeds on schedule, introducing the second commercial lander system to the program and reducing dependence on any single commercial partner. One of the most tangible capability additions planned for Artemis 4 or 5 is the Lunar Terrain Vehicle, a crewed pressurized rover that will allow astronauts to travel beyond the EVA walking range of the landing site. Apollo's lunar roving vehicle reached a maximum distance of approximately 7.6 kilometers from the landing site, constrained by the rule that the crew had to be able to walk back to the lunar module if the rover failed. The Lunar Terrain Vehicle, being pressurized, allows much greater range. Preliminary designs suggest operational ranges of 20 to 30 kilometers per excursion, with the ability to park and wait in emergencies rather than requiring a walking return. NASA awarded development contracts in 2024 to 3 commercial teams. Intuitive Machines partnered with Boeing, Lunar Outpost, and Venturi Astrolab. The vehicle must operate in the extreme thermal environment of the South Pole, functioning across temperatures from -50 to +120 degrees Celsius in sunlit terrain, and must navigate terrain that has never been mapped at the resolution required for safe rover driving. Solar power at the lunar South Pole is challenging. The peaks of eternal light receive nearly continuous sunlight, approximately 94% of the time at Malapert Massif, but they are not located exactly at the most scientifically valuable sites. A mission that requires both access to shadowed craters where the ice is and reliable power faces a geographic tension. Solar panels work best far from shadows, and ice is only in shadows. NASA's Fission Surface Power System, under development in partnership with the Department of Energy, is designed to provide 40 kilowatts of continuous electrical power from a uranium fission reactor deployable on the lunar surface. 40 kilowatts is sufficient to run an in-situ resource utilization electrolysis plant, power a pressurized habitat, charge rover batteries, and operate science instruments simultaneously. The first fission surface power demo unit was targeting a lunar delivery in the late 2020s by commercial lander. If successful, fission surface power transforms the South Pole's power situation from constrained and geographically rigid to abundant and geographically flexible, the enabling technology for everything from sustained surface operations to industrial-scale water extraction. A sustained human presence on the lunar South Pole requires communication and navigation infrastructure that does not yet exist. ESA's Moonlight Initiative and NASA's Lunar Communication and Navigation System planning both target a constellation of approximately 4 to 6 satellites, providing coverage of the lunar South Pole with a positional accuracy equivalent to GPS on Earth, within approximately 10 meters at the surface. This constellation enables surface rovers to autonomously navigate without line-of-sight communications to Earth, enables astronauts to have reliable Earth voice communication from any South Pole surface location, and enables precision landing for future missions without relying solely on the lander's own terrain-relative navigation sensors. Everything that Artemis is building, the navigation systems, the life support experience, the radiation data, the in-situ resource utilization technology, the long-duration surface operations protocols, the crewed nuclear power systems, is equally applicable to a Mars surface mission. NASA's long-term human exploration architecture explicitly frames the lunar return as a Mars proving ground. Technologies that are too risky to test for the first time of 56 million kilometers from Earth can be tested and validated 384,000 kilometers from Earth, where the round-trip communication delay is 2.56 seconds rather than 20 to 40 minutes, and where an emergency return to Earth, while difficult, is measured in days rather than months. A crewed Mars mission will require a life support system that functions reliably for 2.5 to 3 years without resupply, an in-situ resource utilization propellant production system that actually works on another planet's surface, radiation shielding and medical protocols sufficient for 600 to 900 millisieverts, total crew dose, autonomous navigation and landing without real-time Earth guidance, and a crew that can function psychologically and physically in complete isolation for 18 months at minimum. Every one of these requirements has a direct analogue being developed and tested in the Artemis program. Artemis is not a detour on the road to Mars, it is the road. The narrative around Artemis II focused overwhelmingly on what it didn't do. It didn't land, it didn't put boots on a regolith, it didn't plant a flag. But fixating on those absences means missing what Artemis II actually did, and what it actually collected in the way of science data is, in some areas, more difficult to replicate through any other means than the landing itself. The most irreplaceable science from Artemis II is also the hardest to fully publish. The biological data from 4 living human beings in the deep space radiation environment. No animal model fully replicates human radiation response. No Earth-based accelerator simulation fully replicates the high-energy cosmic ray particle spectrum in translunar space. And no mannequin, however sophisticated, generates the physiological stress responses, the immune system changes, the microbiome shifts, and the hormonal dynamics that living human beings experience in this environment. Blood draws taken before, during, and after the mission allow measurement of gamma H2AX, the phosphorylated form of histone H2AX that forms at sites of DNA double-strand breaks within minutes of radiation-induced damage. This biomarker gives researchers a near real-time indicator of DNA damage rate during the mission. Cortisol and DHEA levels measure stress response system function. Telomere length measurements, comparing samples taken before and after the mission, indicate cellular aging acceleration from radiation exposure. NASA's twin study with Scott and Mark Kelly established ISS duration baselines. Artemis II extends those baselines into translunar space for the first time. This biological data will take years to fully analyse. The cancer risk implications, the immune function data, the cognitive performance testing, all of it feeds into the radiation protection standards and medical protocols for every human mission beyond Earth orbit for the next century. Artemis II flew a precisely characterised trajectory and carried instrumentation that measured its actual position against predicted position throughout the mission. The deviation between predicted and actual trajectory, caused by subtle gravitational perturbations from the Moon's non-uniform mass distribution, solar radiation under pressure, and outgassing from the spacecraft, provides data that refines the lunar gravity field models used for all future mission planning. The Moon's gravity field is lumpy. The Grail mission, twin spacecraft that orbited the Moon in 2011 and 2012, produced the highest resolution lunar gravity map ever created. But Grail measured gravity in low lunar orbit, not in the translunar trajectories and near rectilinear halo orbit that Artemis uses. Orion's high-precision navigation data along the free return trajectory adds data points to lunar gravity field characterization in trajectory regimes that Grail never sampled, refining prediction accuracy for the specific orbital paths used by Artemis missions. More accurate gravity models mean more efficient trajectory planning, which means less propellant consumption, which means more payload capacity, which means cheaper missions. The data from Orion's 1,200 plus sensors throughout the Artemis II mission constitutes a comprehensive engineering science dataset. Every structural load measurement during launch, during maneuvers, during lunar flyby, and during re-entry provides validation or refinement of the structural models used to design and certify the vehicle. The heat shield performance data is particularly significant. Post-Artemis I analysis found that some Avcoat ablator blocks showed unexpected char depths and localized hotspots not predicted by pre-flight thermal models. Artemis II's re-entry, with a crew aboard at the standard re-entry profile, provided thermal data validating the corrective model updates made after Artemis I, confirming that those model updates are accurate, before Artemis III commits to a landing mission that cannot be aborted once the surface operations phase begins, was worth the mission by itself from an engineering risk standpoint. At closest approach, Orion flew approximately 7,400 kilometers from the lunar surface. From that distance, crew members observed and photographed the Moon under lighting conditions that surface missions cannot replicate, looking down at a geometry that provides a different perspective on terrain features than either orbital missions, which are too close, or telescopic Earth observation, which is too far and through Earth's atmosphere. The oblique viewing angle provides high-quality stereoscopic imaging of terrain features, particularly the highland and mare boundaries, crater morphologies, and the south polar terrain visible from the trajectory geometry. Human observers detect patterns, unusual surface textures, unexpected colour variations, morphological anomalies that automated imaging systems are not programmed to prioritise. Artemis II crew member reports of surface features noted during the flyby added to the database of observations informing Artemis III landing site selection. The translunar environment sits outside Earth's magnetosphere, exposed to the full intensity of the solar wind, solar energetic particles from solar flares, and the interplanetary magnetic field. Instruments aboard Orion monitoring the space weather environment during Artemis II provided data on the particle and field environment in a regime between the well-characterized near-Earth environment and the well-characterized deep interplanetary environment measured by spacecraft at the L1 Lagrange point. Solar energetic particle events are one of the most serious radiation risks for deep space crews. During a major event, proton fluences can reach levels that would exceed NASA's career limit for unprotected crew members in hours. Predicting these events relies on solar wind monitors at L1, but the approximately 1 hour warning time provided by L1 monitors must be refined with measurements from different vantage points. Artemis II's instrumentation from the translunar trajectory in a different solar longitude than L1 contributed data points to the multi-point space weather monitoring network, improving the physical models used to forecast solar energetic particle events. Better forecasting means better warning time for crews to shelter in storm-protected areas of their spacecraft, a direct safety benefit for every future mission. The data collected by Artemis II, biological, engineering, navigation, observation, and space weather, is not only useful for going to the moon, it's foundational for going further. The radiation biology data is directly applicable to Mars mission planning. The navigation precision measurements feed into interplanetary trajectory design. The space weather monitoring contributes to Sun-Earth connection science, with applications from satellite operations to power grid protection. More broadly, Artemis II demonstrated that humans can survive and function beyond Earth's magnetosphere in the actual deep space radiation environment, aboard a modern spacecraft for mission durations that represent the beginning of the capability required for longer duration missions. That demonstration has scientific value beyond any single data set. It is the existence proof that the next phase of human exploration beyond Earth orbit is physically achievable by human bodies in human machines. The flyby that never landed may, in the long arc of human history, be remembered not for what it didn't do, but for what it first proved was possible. You've made it through the engineering, the physics, the biology, the economics. Now we pull back to the widest possible view. The view from outside the program, outside the decade, outside the century. Because Artemis II, for all its complexity, is part of something much larger than a space program. It's part of the oldest question in human history. What's out there, and can we get to it? And the answer that Artemis II represents is not just yes. Technically, it's something deeper. Something that takes a particular kind of perspective to fully appreciate. When Gene Cernan climbed the ladder of the Apollo 17 lunar module on December 14, 1972, humanity had spent 13 years in an accelerating expansion beyond Earth. From Sputnik in 1957 to Apollo in 1969, the 12 years. The curve of capability was steep, exponential, apparently unstoppable. People in 1972 assumed the moon was the beginning of a trajectory that would reach Mars by the 1980s, the outer planets by the 1990s, perhaps the stars by the 2010s. The arc of exploration seemed obvious. Then it stopped. Not because of physics, not because of technology, because of budget priorities, and a cultural shift in what human societies chose to spend their resources on. For 52 years, longer than most people alive today have been alive, no human being left low Earth orbit. The most capable spacefaring civilization in history chose to stop at the edge of the ocean and stay there. The cost of that 52-year pause is not measurable in dollars, it's measurable in capability lost, institutional knowledge gone, workforce retired, supply chains dissolved, operational experience never accumulated. It's measurable in scientific questions not asked, resources not prospected, technologies not developed, infrastructure not built. And it's measurable in something harder to quantify, the narrowing of what human beings considered possible in space. A generation of scientists grew up never seeing a human being farther from Earth than 408 kilometers. The frontier got smaller in the imagination simply because it was no longer being pushed in reality. Artemis II's crude flyby broke that drought. It proved, with real people in a real vehicle, that the capability still exists, rebuilt, modernized and functioning. That proof, after 52 years of absence, is not a small thing. The Fermi paradox asks, if intelligent life is common in the universe, why haven't we detected it? One of the most sobering proposed answers is the Great Filter. The idea that there exists some barrier in the development of intelligent civilizations that most do not survive. The filter might be behind us. Perhaps the development of complex life is extraordinarily rare. Or it might be ahead. Perhaps most civilizations that reach technological maturity fail to expand beyond their origin planet before some catastrophic event terminates them. A single planet species is, in the long run, a mortal species. The timescales are geological and cosmological, not human lifetime scales, but they are not infinite. The Chicxulub impactor that ended the Cretaceous period 66 million years ago was approximately 10 to 15 kilometers in diameter. An object of that size arriving without warning would end human civilization in hours and human survival on Earth within years. The probability in any given year is approximately 1 in 100 million, vanishingly small, but across centuries and millennia, it is not zero. Human technological capability could, in principle, address some of these risks, but only from a position of multiplanetary capability. Artemis II, one crude spacecraft on a free return trajectory around the moon is not by itself civilization insurance, but it is the beginning of the capability chain that, extrapolated across decades and centuries, leads to a species that is no longer confined to a single point of failure in the cosmos. Consider the scale of time. Homo sapiens as a recognizable species is approximately 300,000 years old. Written history is approximately 5,000 years old. Spaceflight is 68 years old, less than one human lifetime. The first powered aircraft flight was in 1903. The first human in orbit was 1961. 58 years from first flight to first orbit. From first orbit to moon flyby is 62 more years, both compressed to the blink of an eye against 300,000 years of human existence. If human civilization persists for another 300,000 years, a conservative assumption given that we've already lasted that long without modern technology, then every human being who ever lives in that span will inherit whatever foundation we build now. The decisions made in the Artemis era, whether to go, where to go, what to build, or what to learn, are foundation-laying decisions. They establish capability, precedent, institutional knowledge, and legal frameworks that will persist and compound across centuries the way the first settlements, the first legal codes, and the first scientific institutions of earlier eras have persisted and compounded. Artemis II did not land on the moon, but it proved that humans aboard a modern spacecraft can reach lunar distances and return safely. That proof, established by 4 human beings aboard Orion, is now a permanent fact of human history. It cannot be undemonstrated. Whatever budget cycles or program disruptions come next, the fact that Artemis II happened, that people went to the moon's vicinity and came back in the 21st century, is written permanently into the record of what human beings have done. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen were selected for Artemis II from the pool of active NASA and Canadian Space Agency astronauts. Each brought specific expertise: Wiseman's commander experience and operational leadership, Glover's engineering background and ISS experience, Koch's record-setting long-duration spaceflight expertise. She holds the record for the longest single spaceflight by a woman at 328 days on ISS, and Hansen's aircraft systems expertise. These are not symbolic choices alone, they are operational choices backed by technical capability, but they are also undeniably historical choices. Victor Glover became the first black astronaut to travel to lunar distance. Christina Koch, if she proceeds to Artemis III, will be the first woman on the moon. Jeremy Hansen became the first Canadian to travel beyond low Earth orbit. These facts do not make the mission more technically significant. They make it more humanly significant. They expand who the mission belongs to in ways that matter for the sustained cultural investment that a multi-decade exploration program requires. Apollo's crews were all white American men, products of military test pilot culture in an era when those demographics were essentially the only pathway to that career. That was not a moral failing by the individuals involved. It was a structural characteristic of mid-20th century American society. Artemis's crew selection reflects a different society, one that has, imperfectly and incompletely, broadened access to the corridors of technical achievement. Sending a different-looking crew to the moon than Apollo sent is not a reversal of Apollo's value, it's an extension of it. Apollo 11's moon landing on July 20, 1969, was watched by approximately 600 million people, roughly 1 in 6 humans alive at the time. The broadcast reached audiences in 33 countries simultaneously. Surveys taken in subsequent decades consistently show that people who were children when Apollo 11 landed were disproportionately represented among the engineers, scientists, and explorers who carried science and technology forward in the following generation. The causal link between watching a human being walk on the moon and choosing a career in a technical field is not a myth. It's a documented sociological phenomenon. Artemis II's launch and mission were watched by hundreds of millions of people worldwide, across streaming platforms, broadcast television, and social media. The crew's live transmissions from translunar space, images of Earth growing small against the blackness, of the moon's surface visible at closer range than any human eyes had seen in 52 years, reached audiences who had never experienced anything like it. The children who watched Artemis II will be in their 20s and 30s when Artemis III lands. Some of them will be engineers working on the mission. Some of them will be astronauts who later travel farther. The return on the investment of inspiring a generation is not measurable in mission year accounting. It's measurable in the scientists, engineers, doctors, and explorers who choose their lives' work because they were told, by watching real human beings do extraordinary real things, that the universe is a place worth understanding and exploring. All of the engineering, all of the physics, all of the biology, all of the economics, they all ultimately collapse into a single question. The question that Artemis II advanced but did not finally answer, the question that Artemis III is building toward, and the question that will define what the 21st century means in the arc of human existence. Can we become a species that lives beyond its birth planet? Not visits, not flybys, not flags and footprints missions that end with a splash in the Pacific Ocean, but actually lives, maintains, builds, grows, and eventually thrives beyond the 12,742-kilometre diameter ball of rock and water and air that every human being in history has ever called home? We don't know the answer yet. Artemis II moved us one step closer to finding out. The heat shield worked, the life support worked, the crew survived and returned, the data is being analysed, the next vehicle is being prepared, the next crew is training, the trajectory toward the surface is being computed. The moon is not the destination. It's the first question in a much longer conversation. And for the first time in 52 years, human beings are back in a position to ask it, not from the comfortable safety of low Earth orbit, not from the pages of a mission concept document, but from a real capsule in real deep space, surrounded by the real radiation of the real cosmos, asking the real universe whether it's ready to receive us. Artemis II didn't land on the moon, but it proved we're still trying to get there. And in the vast silence of 52 years, that proof is everything. To fully appreciate what Artemis II accomplished, it helps to sit with the sheer improbability of the task from a standing start. Every component of the mission had to function in a sequence of events that could not be rehearsed in full, because no full rehearsal is possible. You can test engines on the ground, you can test life support systems in chambers, you can simulate trajectories in software, but you cannot test a complete crewed lunar mission without flying a complete crewed lunar mission. The variables compound in ways that ground testing cannot replicate. The precise interaction between the crew's biological output and the vehicle's environmental control system at lunar distances, the specific acoustic environment inside Orion during every phase of flight, the exact thermal gradients across the service module during the translunar coast when the vehicle is rotating slowly to distribute solar heating. These are emergent behaviours of a complete system in a specific environment that only manifest in flight. NASA calls this phenomenon system-level integration behaviour. Engineers who have spent years designing individual subsystems are sometimes surprised by how those subsystems interact in the actual operating environment. This is not a failure of engineering. It's the fundamental nature of complex systems. The Apollo program dealt with it constantly. The Apollo 11 mission itself encountered a program alarm, 1202 executive overflow, during the lunar descent that had never appeared in simulation, and the crew and mission control had approximately 10 seconds to decide whether to abort or continue. They continued. but only because the training program had specifically prepared mission controller Steve Bales to recognize that particular alarm as non-critical. That institutional knowledge, that specific preparation, was built through the prior Apollo missions. Artemis II serves the same function. It builds the specific institutional knowledge that only a real crewed mission in the real environment can generate. Think about what mission control in Houston was doing during Artemis II. Not just monitoring telemetry from 370,000 kilometers away, building mission rules, learning in real time what the nominal operation of every system looks like in the actual deep space environment. Because nominal is not something you can fully define from the ground. Every time a system operates in a new environment, it establishes a baseline, and only by watching it operate can you define what deviating from baseline actually looks like. Mission controllers during Artemis II were calibrating their own intuition, developing pattern recognition for what Orion's telemetry streams look like when everything is working correctly. That calibration, that baseline, is what allows mission control to recognize an anomaly instantly when the next mission flies. Without Artemis II, Artemis III's mission control would be comparing actual behavior to paper models. With Artemis II, they're comparing actual behavior to actual behavior. The difference in response speed and confidence during an anomaly could be the difference between a crew that gets good advice in time and a crew that doesn't. The psychological dimension of mission control for deep space is also qualitatively different from ISS operations in ways that only become apparent through experience. On ISS, the philosophy is that mission control can and should be deeply involved in real-time decisions. The latency allows it. The culture supports it. Mission controllers for ISS think of themselves as an active part of the crew, a sixth or seventh person in the loop. At lunar distances, that relationship has to change. The communication delay forces a philosophical shift. Mission control transitions from real-time partner to strategic advisor. Advice is formulated, transmitted, and by the time it arrives, the crew has either already resolved the situation or needs to resolve it themselves, because the next advisory cycle won't arrive in time. Artemis II was the first opportunity for the current generation of mission controllers, most of whom have spent their careers on ISS, to practice that different philosophy with a real crew at real lunar distances. The shift in mindset that the mission produced in the mission control team is not measurable in telemetry, but it is as real an output of the mission as the radiation dosimetry data. There's another dimension of Artemis II that's rarely discussed in the popular coverage: the mission's role in training the crew for what comes next. Artemis II's 4 crew members, or at least some of them, are expected to fly on subsequent Artemis missions. Reed Wiseman and Christina Koch have been mentioned in connection with future assignments, the experience of translunar flight, of seeing the Earth from 370,000 kilometers, of operating Orion systems in the actual environment, of experiencing the thermal and acoustic and radiation environment of deep space. This experience is not something you can purchase in a simulator. The crew of Artemis II, by having flown to lunar distance and returned, carries a kind of knowledge that every other active astronaut lacks. They know what it's like, not what the simulation says it's like, what it actually is. That knowledge, held in their bodies and their nervous systems and their experiential memory, is irreplaceable preparation for the next phase of the program. This is one of the subtler arguments for the crude flyby structure. You could have sent a differently assembled crew on Artemis II, perhaps people who are not planning to fly on subsequent missions, and harvested the same engineering validation data. But by sending people who may fly again on later Artemis missions, NASA builds experiential continuity across the program. The crew of Artemis II, having felt the silence of deep space, having watched the Earth shrink to a blue marble and then grow again on the return, having lived inside the Orion capsule for 10 days at the frontier of human exploration, brings something to the planning of every subsequent mission that no amount of ground-based training can replicate. They become consultants on reality, people you call when you want to know what it actually feels like, what actually surprised you, what actually matters that the engineering documentation doesn't capture. The international dimension of Artemis II's crew selection deserves more attention than it typically receives. Jeremy Hansen's presence as a Canadian astronaut on the first crewed deep space mission since Apollo 17 is not merely symbolic. It is the physical embodiment of a changed arrangement for human space exploration. Apollo was a unilateral American achievement conducted in competition with the Soviet Union, with other nations as observers rather than participants. The ISS era introduced genuine international partnership at the operational level, but the ISS partnership is essentially a Soviet-era relationship carried forward, Russia as a co-equal partner, other nations as contributors but not equals. The Artemis international architecture is something different again. A US-led framework with European, Japanese, Canadian and other partners as genuine contributors at the hardware level, with reserved crew seats as the tangible expression of that contribution. Hansen's mission is the proof of concept for that arrangement. Canada contributed Canadarm3 to Gateway. Canada received a crew seat on an early Artemis mission. The transaction is transparent, the value is concrete, and the diplomatic signal is unmistakable. This is how you buy a seat at the table of human deep space exploration in the 21st century. For every other space agency watching, and they were all watching, Hansen's mission provided the proof that the Artemis Accords framework is real, that the commitments are honoured, and that contributing to the program yields tangible returns. That signal has consequences that extend far beyond the specific technical contribution of Canadarm3. It pulls other nations toward the Artemis framework and away from the competing International Lunar Research Station framework that China and Russia are offering. The battle for international partners in space is real, the stakes are high, and Artemis II was a data point in that battle. The rocket that launched Artemis II deserves one more moment of consideration, because the SLS's existence is itself the product of a set of decisions that continue to reverberate through the program. When NASA's Constellation program, the previous attempt at a moon return, was cancelled by the Obama administration in 2010, it was in the middle of developing the Ares 1 crew launch vehicle and the Ares 5 heavy lift rocket. The Augustine Commission, which reviewed the program and recommended cancellation, noted that Constellation was underfunded relative to its ambition, relying on a schedule that required more funding than Congress was providing, and was at risk of becoming a program that cost vast sums while making limited progress toward actual human, deep spaceflight. The SLS emerged from the wreckage of Constellation as a congressional mandate, driven partly by the desire of specific congressional members to protect aerospace jobs in their districts, and partly by a genuine belief that a government-owned, heavy launch capability was strategically important independent of commercial alternatives. The SLS reused space shuttle infrastructure, the RS-25 engines, the solid rocket booster technology, the Michoud assembly facility in New Orleans, the manufacturing expertise at Marshall Space Flight Center in Huntsville, Alabama, in ways that preserve the workforce and the industrial base while adapting them to a new vehicle. The result is a rocket that is simultaneously the most powerful operational launch vehicle in history and the most expensive single-use machine ever built. The tension between those two facts defines the SLS's life. Its defenders argue that its unique capability, the ability to put Orion and a trans-lunar injection set on a trajectory to the moon in a single launch, justifies its cost because the alternative is an architecture that requires orbital assembly, propellant transfer and multiple commercial launches before a mission can begin. Its critics argue that Space's Starship, once operational, will provide comparable or superior capability at a fraction of the cost, making the SLS a transitional vehicle at best and a money sink at worst. Both positions contain truth. The SLS is real, operational and capable today, and today matters when 4 human lives depend on getting to the moon. Starship is real in development and increasingly capable, but not yet human-rated for deep space, not yet capable of the orbital refueling operations its lunar mission profile requires, and not yet proven at the operational cadence that a sustained lunar program needs. The SLS may indeed be a transitional vehicle, serving the program through Artemis 3 or 5 before commercial alternatives mature. But transitional doesn't mean unimportant. Without the SLS, there is no Artemis II. Without Artemis II, there is no path to Artemis 3. The transitional vehicle that gets the program through the gap between today's capability and tomorrow's better option is as essential as the eventual better option itself. Understanding the heat shield's performance in more detail reveals something remarkable about engineering conservatism and its trade-offs. When NASA specified the thermal protection requirements for Orion's heat shield, they used worst-case scenarios: the fastest possible reentry angle, the highest possible velocity, the most intense solar activity, and the worst-case atmospheric density profile. The resulting specification drove the use of Avcoat ablator at a thickness that would handle all of those conditions simultaneously. In reality, no single re-entry will hit every worst case simultaneously. But engineering for worst cases is not waste. It's the philosophy that produced a heat shield that survived when it performed differently than predicted during Artemis I. Here's the specific technical issue. During Artemis I's re-entry, approximately 60 blocks of Avcoat ablator material were lost, sheared off during the high dynamic pressure phase of re-entry rather than ablating away gradually as designed. Post-flight analysis traced the anomaly to the specific conditions of Artemis I's re-entry profile, which was a non-standard trajectory used to maximize data collection during the test flight. The blocks that were lost were in areas of higher than predicted aerodynamic shear. The underlying heat shield structure was not compromised. The depth of ablation in those areas was within design margins even after the block loss. But the anomaly required investigation, and the investigation produced a revised understanding of the ablator's behaviour under high shear conditions. Artemis II's re-entry on a more standard crew return trajectory validated the revised model. The heat shield performed within the updated predictions. That validation, the confirmation that the revised model is correct, is not flashy. It doesn't appear in mission highlight reels, but it is the kind of engineering advancement that prevents the kind of tragedy that ended Columbia. The Columbia disaster is worth dwelling on for a moment in the context of Artemis, because the lessons of Columbia are woven into the fabric of how Artemis manages risk in ways that are invisible from the outside but profound in their operational consequences. Columbia was destroyed on February 1, 2003, because a piece of foam insulation broke off the external tank during launch and struck the leading edge of the left wing, creating a breach in the thermal protection system. During the 16-day mission, engineers at the Johnson Space Center who were aware of the foam strike raised concerns about potential damage and a requested satellite imaging of the wing. Their requests were not fulfilled, partly due to organizational dynamics that discouraged the transmission of potentially bad news up the management chain. When Columbia re-entered, superheated plasma entered through the breach, and the vehicle broke apart over Texas and Louisiana. All 7 crew members were killed. The Columbia Accident Investigation Board found that the accident had 2 root causes: the technical cause, which was the foam strike, and the organizational cause, which was a safety culture that failed to take seriously the concerns of engineers who identified a potential problem. The board's recommendations included fundamental changes to NASA's safety culture, mandatory processes for elevating concerns, required responses to dissenting technical opinions, and explicit protection for engineers who raised safety issues, regardless of schedule or cost implications. Artemis is built in the aftermath of those recommendations. The processes that govern Artemis decision-making are deliberately designed to surface dissenting views, require responses to technical concerns, and impose schedule costs for safety investigations that would previously have been minimized in the name of mission timelines. This is partly why Artemis takes longer than it might otherwise. The safety culture is real, and it has real schedule implications. But it is also why Artemis II flew with a crew aboard rather than suffering a catastrophic failure that might have ended the program. The anomalies identified during Artemis I were investigated seriously, the corrective actions were validated, and only then did Artemis II fly with human beings inside. Columbia's crew died because that process failed. Artemis II's crew lived because it worked. The public often underestimates the role of mission rules in human spaceflight safety. Mission rules are pre-established decision criteria, specific numerical binary conditions that determine whether a mission proceeds or aborts at each decision point. For Artemis II, the mission rules document ran to hundreds of pages, covering every phase of flight and every credible failure mode. A mission rule might state, if the delta pressure across the cabin pressure vessel falls below X kilopascals per hour, abort the translunar injection burn and return to Earth. Another might state, if any two of the four main parachutes fail to deploy, the vehicle can still land safely, but if three fail, command the crew to brace for impact and activate emergency systems. These rules are not written during the flight. They are written during years of pre-mission analysis, tested in simulators, refined through expert review and locked before launch. Their purpose is to remove decision-making under pressure from the crisis moment itself. The value of this approach is most obvious when something goes wrong, and the crew has seconds to decide whether to continue or abort. If they have to think through the consequences of the anomaly from first principles under stress, they will take longer, make more errors, and be more susceptible to cognitive biases, including optimism bias, the tendency to believe that things are going to be okay even when they probably aren't. Mission rules short-circuit that process. The decision is already made. The crew's job in an anomaly is not to decide what to do. It's to identify which mission rule applies and execute the prescribed response. The engineering and analysis that went into writing that rule is better than anything the crew can do in real time under stress. Trusting the rules is not passivity. It's epistemically correct deference to the calmer, more thorough thinking that happened before the stress began. Artemis II's mission rules were written partly based on Artemis I data and partly based on legacy Apollo and Shuttle data. After Artemis II returned, the mission rules for Artemis III were revised based on what Artemis II revealed. Cases where the predefined thresholds were too conservative, cases where they were not conservative enough, and cases where new failure modes were identified that hadn't been anticipated. This iterative refinement of mission rules is one of the most concrete and least celebrated outputs of a crewed test flight. The rules that will govern whether Artemis III proceeds to a lunar landing or aborts at the Gateway are better rules because Artemis II flew, and better rules mean a crew that is safer, not because the technology improved, but because the decision framework improved. The crew training program for Artemis II lasted approximately 2 years and covered every aspect of the mission in extraordinary depth. The 4 crew members trained in high-fidelity Orion simulators that replicated the vehicle's exact flight software, its cockpit layout, its system response times, and its failure modes. They trained in neutral buoyancy facilities, underwater environments that simulate microgravity, practicing procedures for every operation they would conduct in flight. They trained in vacuum chambers. They trained in centrifuges to replicate the G-forces of launch and re-entry. They trained in wilderness survival for the contingency of a spacecraft returning to an unexpected location after re-entry. They flew training aircraft to maintain piloting proficiency. They underwent medical training that gave each crew member the ability to provide basic emergency care to every other crew member, because in deep space, the doctor is the person next to you, not a flight surgeon on the ground. The psychological component of crew training is equally intensive and far less visible. The 4 crew members of Artemis II underwent years of team cohesion training, exercises designed not just to teach them procedures, but to build the trust, communication patterns, and conflict resolution skills that allow a team of 4 people to function effectively under extreme stress in an extreme environment for 10 days without degradation of decision quality or interpersonal function. The research on team dynamics in isolated, confined, and extreme environments, including from Antarctic expeditions, submarine crews, and analog spaceflight environments like the Hera isolation habitat at Johnson Space Center, consistently shows that the most important predictor of mission success is not individual crew member skill, it's the quality of the team's communication and trust. NASA's Behavioral Health and Performance team worked with the Artemis II crew throughout their training to build that quality systematically, using tools drawn from organizational psychology and peak performance research. And then, when the day came, when the SLS engines lit and the solid rocket boosters fired and the launch tower fell away and 39 million newtons of thrust pushed 4 human beings skyward at a rate that compressed time, all of that training, all of those mission rules, all of those simulated emergencies and practices, procedures and rehearsed decisions crystallized into action. Not thought, action. The kind of fluid automatic competence that only comes from preparation, so deep it bypasses conscious reasoning and runs straight from perception to response. The 8-minute ascent from Kennedy Space Center to low Earth orbit is one of the most violent rides in human experience. The G-forces climb steadily as propellant is consumed and the vehicle grows lighter. The noise inside the capsule during the first 126 seconds, while the solid rocket boosters are burning, is approximately 120 decibels, comparable to standing next to a jet engine on a runway, despite the acoustic dampening in the crew suits and the vehicle structure. The vibration is felt in the bones, in the teeth, in the joints. And then, approximately 126 seconds after liftoff, the solid rocket boosters separate with a jolt, and for a moment the ride smooths, before the core stage RS-25 engines, still burning, push the stack forward and upward through the thickening deceleration as the atmosphere thins. 8 minutes after launch, the RS-25 engines shut down, main engine cut off, the crew is in orbit, the roar is gone, the vibration is gone. Everything that was loud and violent and relentless is suddenly, completely silent, and the Earth is already 160 kilometers below, curving visibly at the edges of the windows, the blue of the oceans and the white of the clouds and the brown of the continents visible all at once in a way that no human eye evolved to see. The crew of Artemis II had seconds to absorb this before the mission clock demanded their attention. But those seconds, the first seconds of weightlessness, the first seconds of genuine space, the first view of Earth as a sphere rather than a landscape, those seconds don't leave you. They become part of how you see the world for the rest of your life. The translunar injection burn came hours later, after the crew had completed the initial checks, after the vehicle had been inspected, after mission control had confirmed that every system was nominal. The interim cryogenic propulsion stage ignited, and Orion accelerated from its circular low Earth orbit toward the Moon. The burn lasted approximately 18 minutes, consuming all of the ICPS propellant and increasing the vehicle's velocity by approximately 3,100 meters per second. When the ICPS separated, Orion was no longer in orbit around the Earth. It was on a trajectory toward the Moon, and nothing, short of its own engine, could bring it back on any reasonable timeline. The point of no early return was not a moment. It was a gradual realization as the Earth in the windows grew visibly smaller with each passing hour. The 3.5-day coast from Earth to the Moon is perhaps the least dramatic and most profound phase of the mission. There is no engine burn. There is little the crew can do to change what happens next. The Moon's gravity is gradually taking over from Earth's, and the vehicle is simply following the physics, tracing the precise arc that orbital mechanics dictated from the moment of the translunar injection burn. During this coast, the crew exercised, ate, slept, monitored systems, and looked out the windows at an Earth that was already too small to make out individual continents clearly. They were farther from home than any human beings in more than half a century, and every hour they were farther. The lunar flyby itself, the moment of closest approach, when Orion swept to within 7,400 kilometers of the surface, lasted only minutes in the sense of the dramatic minimum distance, but was experienced across hours as the vehicle swept around the Moon on its free return trajectory. The crew saw the lunar surface below them at closer range than any human eye had seen it since Apollo 17. They saw the South Pole, the target of the missions to come, with a clarity that no telescope and no orbital camera can fully replicate through human perception. The permanently shadowed craters were black absences in a grey landscape. The peaks of eternal light caught the low-angle sun and gleamed against the darkness. The terrain was ancient and cratered and utterly alien, and yet somehow, in some way that none of them could have predicted from any amount of study, recognizable, not as familiar, but as real. Real in a way that photographs aren't. Real in the way that only direct perception makes things real. And then they were past it. The moon fell behind. The return coast began. 3.5 more days, the Earth growing larger in the windows now, the journey reversing its geometry as gravity pulled them home. The re-entry, when it came, was everything the engineering said it would be. Violent, loud, hot and brief. The parachutes deployed. The capsule slowed, and 4 human beings splashed into the Pacific Ocean, alive, having gone farther than any of their species in 52 years, and come back with data, with experience, and with the lived knowledge that the path forward was real. The splashdown recovery, the moment when the capsule bobs in the Pacific and the recovery teams move in, is itself a technology demonstration. The US Navy and NASA recovery teams that retrieved Orion's crew after Artemis II practiced and refined procedures that had not been operationally used in decades. The Apollo era had extensive ocean recovery capability, built around Navy frogmen and recovery ships and helicopters that were all part of a standing infrastructure. After Apollo, that infrastructure largely dissolved. Recovering the space shuttle Orbiter required a landing strip, not a recovery fleet. The rebirth of ocean capsule recovery for the Artemis era, including the specialized personnel, the recovery vessel, the medical protocols for treating crew members immediately after ocean recovery, and the procedures for quickly assessing spacecraft condition in a marine environment, is itself a capability that had to be rebuilt from partial documentation and institutional memory. The Artemis II crew, when they emerged from the capsule after recovery, had bodies that had been through 10 days of deep space. Their cardiovascular systems had partially deconsolidated. Their leg muscles, under tax by 10 days of microgravity, needed careful management during the first hours back in full gravity. The reflex of balancing, of walking, of orienting to gravity had to be re-engaged, not painfully, not dangerously, but carefully. The medical teams that received them were following protocols developed from ISS recovery experience and refined for Artemis-specific mission duration and trajectory. Each crew member underwent immediate medical assessment, blood draws for the post-flight biological sample collection, and cardiac monitoring for the first hours after recovery. The data from that immediate post-flight period, how quickly heart rate normalized, how balance reflexes responded, how immune markers changed in the first hours after return, adds to the baseline that informs crew recovery protocols for longer duration missions. In the days and weeks after Artemis II's crew returned, the real work of the mission began, the analysis. Thousands of engineers across NASA and its contractor network processed the mission's data. Heat shield engineers analysed the temperature gradient measurements from re-entry. Life support engineers analysed the atmospheric chemistry data from the 10-day mission. Navigation analysts compared the actual trajectory against predicted trajectories and updated gravity field models. Radiation scientists processed the dosimetry data and the biological samples. Sleep researchers analysed the actigraphy data, and somewhere in the middle of all of that analysis, the picture of what Artemis III would look like came into sharper focus, because the picture of what Artemis II was became clear. This is the deepest value of test flight programs in human spaceflight. Not the individual data points, but the calibration of the entire modelling and simulation infrastructure against reality. Every simulation of every system run before Artemis II flew made predictions. Artemis II provided measurements. The comparison between predictions and measurements is not primarily about identifying failures. It's about identifying the places where the models were approximately right, the places where they were systematically wrong in predictable ways, and the places where the behaviour was genuinely unexpected. The first category validates the existing models. The second allows systematic correction of the models. The third, the genuinely unexpected behaviours, is where science advances, where engineering understanding deepens, and where the most important learning occurs. Artemis II generated examples in all three categories, and the ongoing analysis of those examples is shaping every subsequent mission in the program. The trajectory toward Artemis III, as it stands after Artemis II, is clearer than it was before. The pieces are in development. The Starship human landing system continuing its test flight program, the Gateway power and propulsion element and habitation and logistics outpost in production, the surface spacesuits in advanced development, the candidate landing sites narrowed to 13 regions near the lunar South Pole. The timeline is constrained by the Starship development timeline above all else. If the Starship is not certified for crewed lunar landing, Artemis III cannot launch, regardless of how ready Orion and the SLS are. But the trajectory is real, the momentum is real, and the institutional will, shaped by Artemis II's success, is real. Every day that passes after Artemis II, engineers are building the lander that will take the first Artemis crew to the surface. Every day, mission planners are refining the surface operations procedures. Every day, the candidates for the Artemis III crew, whoever they ultimately are training in simulators and neutral buoyancy tanks and psychological cohesion programs for a mission that will be the first human landing on the moon since 1972. When that day comes, when the Starship's engines light above the South Pole and the vehicle descends on its column of fire toward a surface of ancient grey rock, the first footstep that breaks that surface will be paid for by decades of work, including the work done by Artemis II in proving that the path there is survivable. The South Pole of the Moon, when humans first stand on it, will look unlike anything in the Apollo record. The equatorial landing sites of Apollo, Tranquility Base, the Ocean of Storms, Fromoro, the Hadley Apennine region, the Descartes Highlands, Taurus Littrow, were relatively flat, relatively well lit, relatively unchallenging terrain by lunar standards. The South Pole is none of those things. It is a landscape of extreme contrast, brilliant white-lit ridges adjacent to absolute black crater interiors of ancient terrain that has not been geologically active for billions of years, of a sky in which the sun sits permanently near the horizon and casts shadows that stretch for kilometers from even modest boulders. The first humans to stand there will be standing in a place that makes every previous human landscape seem almost familiar by comparison. And they will be standing there, if everything proceeds as designed, because Artemis II flew. Because 4 people rode a rocket more powerful than the Saturn V to a point 370,000 kilometers from Earth and came back alive. Because the heat shield worked, and the life support worked, and the navigation worked, and the people worked, together, in a capsule smaller than a parking space, at the absolute frontier of what any member of our species has ever done. Because 52 years of absence ended with a crude flyby that proved the capability still existed, still functioned, still could be trusted with human lives, and still pointed forward toward a future that the mission itself was not yet ready to reach. The mission they sold you and the mission they flew were different, but the mission they flew was, in its own way, the more important one. Not because a flyby is more valuable than a landing is more valuable, and it will come, but because a flyby that proved the path was clear is what makes the landing possible. You can't skip steps in this business, not when the steps are made of physics and the price of failure is measured in human lives. The architecture was right, the sequence was right, the mission was right. Artemis II didn't land on the moon because it wasn't supposed to, and that restraint, that deliberate discipline commitment to doing things in the right order, to validating before escalating, to building the foundation before adding the next floor, is precisely what makes everything that comes after it possible. The moon will be there when Artemis III arrives. The permanently shadowed craters will hold their ice in cold silence for another few years while the landing system is certified. The South Pole will wait, as it has waited for 4 billion years, for the first human footstep. But this time, for the first time since 1972, the question is not whether humans will go back. It's only a question of when. Artemis II answered the weather. The rest is engineering. There's a particular kind of courage embedded in a mission like Artemis II that doesn't get named as courage because it doesn't look like the courage we're used to celebrating. The courage we celebrate in spaceflight is the courage of the crew, the willingness to strap into a vehicle on top of millions of kilograms of explosive propellant and trust that the engineering is right. That courage is real and it should be honoured. But there's another courage in the Artemis program that operates at the institutional level, and it's the courage to go slowly when the world is demanding you go fast. Every instinct in public life pushes space programs to accelerate, to deliver dramatic results, to give the press and the public something compelling to show. The cancellation of Constellation was partly driven by the perception that the program was going too slowly, spending too much, and not delivering anything impressive enough to justify its cost. The pressure on Artemis to show progress, to do something dramatic, to plant a flag, to give people a moment they could put on the evening news, is constant and real. The decision to fly Artemis II as a crewed flyby rather than a crewed landing attempt was, in some sense, a decision to resist that pressure. To say, we know what you want to see, and we are not going to give it to you before the engineering says it's safe to try. That institutional courage, the courage to do the next right thing rather than the next impressive thing, is one of the hardest things to sustain in any large public program. It requires leadership that can explain complexity to audiences that prefer simplicity, that can defend methodical progress against critics who see caution as timidity, and that can maintain a long-term vision through the short-term cycles that determine annual budgets. NASA's leadership during the Artemis program has had to exercise that kind of courage repeatedly, in defending the SLS against critics who wanted to skip straight to commercial alternatives, in defending the Gateway architecture against critics who wanted to go directly to the surface without an orbital way station, and in defending the Artemis II crewed flyby architecture against critics who wanted to attempt a landing on the first crewed flight. In each case, the defenders of the architecture could point to specific engineering reasons why the conservative path was the correct one. In each case, the critics could point to the costs, financial and schedule, of that conservatism. And in each case, the defenders were right in the way that matters most. No crew member died. The heat shield didn't fail. The life support didn't fail. The systems that were supposed to work worked, and the systems that revealed unexpected behaviours revealed them in ways that were survivable and correctable. The methodical approach produced a methodical success. And now, with that success in hand, the next step can be taken, not because the schedule demands it, but because the engineering supports it. There's one more thing worth saying about the 52-year gap between Apollo 17 and Artemis II, and it's something that tends to get lost in the technical discussions and the economic arguments. This gap was a choice, not a single choice made on a single day, but a sustained, repeated choice made by democratic societies across half a century to spend their resources on other things: healthcare, infrastructure, defense, social programs, consumer goods, the ordinary priorities of ordinary life in prosperous societies. Those choices were not wrong. They reflected real human needs and real human preferences. But they had a cost, a specific cost, which is that the frontier of human presence in the cosmos did not advance for 52 years. The question of whether that was the right trade-off is genuinely complicated. The resources that did not go to human deep space exploration went to things that benefited billions of people in tangible, immediate ways. The resources that did go to human spaceflight, the ISS, the shuttle program, produced real scientific and technological value. But what was lost in the 52-year absence from deep space is harder to quantify. The knowledge not accumulated, the technologies not developed at pace, the institutional capabilities that atrophied, and perhaps most importantly, the human sense of possibility that contracts when the frontier stops being pushed. Artemis II is, among many other things, a statement that the trade-off has been reconsidered, that some portion of democratic society's resources is again being directed at the frontier, that the calculation has shifted, perhaps because of China's emergence as a competitor, perhaps because commercial space has changed the economics, perhaps because the coalition supporting space exploration has broadened. The reasons are less important than the result. Humans went back to lunar distance and the program is building toward a landing. The 52-year pause is not forgotten, but it is over. What comes after Artemis III will determine whether the Artemis era is remembered as the successful return to the moon or as the beginning of something larger. The program's trajectory as designed points toward permanent human presence on the lunar South Pole, ISRU propellant production, a gateway station that operates continuously with rotating crews and eventually missions to Mars. Each of those steps is contingent on the previous one succeeding and on sustained financial commitment across multiple presidential administrations and multiple congressional sessions. That sustained commitment is not guaranteed. Programs of this scale and duration have been cancelled before. Constellation was one of them. The Space Exploration Initiative of the early 1990s was another. What makes Artemis more likely to survive is the combination of factors that distinguish it from those predecessors. The international partnership commitments that add cost to cancellation, the commercial investment that creates private sector stakeholders with lobbying power, the existence of competing programs from China that provide motivation for sustained investment, and the genuine technical progress that accumulates with each mission and makes the program harder to abandon as more has been accomplished. Artemis II added to that resilience. It added an international crew member whose nation is now deeply invested in the program's success. It added commercial partnerships in the recovery operation and mission support. It added a demonstrated success that any future administration would have to reckon with in justifying a cancellation. The Moon, when humans next stand on it, will be different from when we last left it. Not geologically, the Moon's geological quiescence means that the Taurus-Littrow Valley, where Gene Cernan planted the last human footprint in 1972, is essentially unchanged. The footprint preserved in the airless, weatherless surface exactly as Cernan left it. But the Moon will be different in context. Humanity will be different. We will arrive with tools that Apollo could not have imagined. Real-time, full-colour, high-definition video transmission, autonomous rovers with artificial intelligence navigation, in-situ resource utilisation technology ready for testing, materials that are lighter and stronger than anything the Apollo engineers had access to, and a body of knowledge about human physiology in space that has accumulated across 24 years of continuous ISS operations. We will arrive knowing more about where we are going, more prepared for what we will find, and more capable of doing something lasting with what we find than any Apollo crew could have been. And we will arrive because of Artemis II, because of a mission that didn't land but proved that landing was possible, because of 4 people who rode the most powerful operational rocket in history to the edge of the inhabited universe and came back alive, carrying data that made the next mission safer and the one after that possible, and the one after that imaginable. The mission they flew was not the mission the headlines described. It was something more disciplined, more foundational, and more important. It was the proof of concept for everything that comes next. The flyby that the world half noticed and half misunderstood may be the most consequential single mission in the history of human spaceflight since Apollo 11. Not because of what it did, but because of what it enabled. Not because of the flag it planted none, but because of the ground it prepared. The Moon is waiting, the program is building, and Artemis II, unremarkable in its restraint and extraordinary in its consequence, pointed the way. The physics of what Artemis II accomplished cannot be separated from the human meaning of it, and the human meaning cannot be separated from the historical moment in which it occurred. We live in an era of simultaneous technological acceleration, a time when the tools for reaching beyond Earth are advancing faster than at any point since Apollo, and when the will to sustain the effort required to actually reach beyond Earth is contested in ways Apollo never faced. The Cold War provided Apollo with something the Artemis program has to manufacture through harder means, a clear existential national purpose that united factions behind a single goal with a single deadline. Win the space race, beat the Soviets, land a man on the Moon before the decade is out. Kennedy's famous commitment at Rice University in 1962 was not just rhetoric, it was a mobilization order, backed by the resources and the consensus required to actually accomplish the thing. Artemis has no equivalent unifying moment. It has competition with China, but it's a slower, more complicated competition than the Soviet threat. Without the immediacy of intercontinental missiles and the existential stakes of nuclear confrontation. It has scientific objectives, but science has never by itself sustained a program at this scale against the budget pressures of a democratic government. It has commercial partnerships, but commercial partners optimize for return on investment in timescales shorter than lunar programs operate on. What Artemis has, that Apollo also had but didn't need as urgently, is the case for human survival. The long-duration argument that a species confined to one planet is a species with an expiration date. That argument is not new. It has been made by Carl Sagan and Stephen Hawking and Elon Musk and dozens of others. It's intellectually compelling but emotionally distant. The threats it points to operate on timescales of thousands or millions of years, not the next election cycle. What Artemis II did, perhaps more than anything else, is make the program feel possible in the present tense, rather than aspirational in the future tense. It's one thing to say we should become a multiplanetary species. It's another to watch 4 human beings ride to the moon and come back successfully in the year you're living in. The first is philosophy. The second is news. And news, unlike philosophy, has the power to shift what people believe is real, what they believe is possible, and what they're willing to support with their votes and their tax dollars. Every generation needs its demonstration of what human beings can do when they work together toward a hard, clear goal. The generation that watched Apollo had that demonstration. The generation that grew up between Apollo and Artemis did not in space exploration, not in the direction of the frontier, not in the particular register of human achievement that space represents. Artemis II gave the current generation its first glimpse of that register. Not a full view, not a landing, but a glimpse, enough to know that the scale of ambition is real, that the engineering is working, and that what comes next is not a fantasy. When Artemis III lands at the south pole of the moon, it will not surprise the people who watched Artemis II. It will feel like the next thing that was supposed to happen, because Artemis II made it feel plausible. That shift in what feels plausible, that change in baseline expectation, is one of the most powerful things a demonstration mission can accomplish, and it's one of the things Artemis II accomplished most completely. The moon is closer now than it has been in 52 years, not in distance. It orbits at the same average 384,400 kilometers it always has, but in the particular sense of closeness that comes from human presence, from the knowledge that living human beings have recently been in its vicinity and returned safely, from the institutional readiness that has been rebuilt and validated. Artemis II closed that distance, not all the way, but enough to see the path clearly from here to there, enough to know that the engineering is ready, enough to believe, on the basis of demonstrated evidence rather than optimistic projection, that the next crew that goes there will not only reach the moon, they will land on it. The question that framed this entire story, why didn't Artemis II land on the moon, has an answer that is at once technical and architectural and physiological and historical and economic and philosophical. The technical answer is that landing requires a separate vehicle that wasn't ready. The architectural answer is that the program was designed as a sequence of escalating capability tests, and landing was always the third test, not the second. The physiological answer is that you cannot land humans on the moon in a vehicle whose crude behaviour hasn't been validated in the actual deep space environment. The historical answer is that 52 years of absence required a deliberate reconstruction of capability before the most demanding task could be attempted. The economic answer is that the cost of a failed first crewed landing, in lives, in program continuity, was too high to risk before the validation flight had been completed. And the philosophical answer is that the wisest thing is sometimes not the most impressive thing, and programs that try to skip wisdom in pursuit of impressiveness tend to end in tragedy. All of those answers are true, and together they add up to a simple statement. Artemis II didn't land on the moon because everything that makes landing on the moon possible had to be proven first. And now it has been. The path forward is clear, the engineering is validated, the crew is trained, the world is watching, and somewhere in a mission control room that smells of coffee and electronics and the particular intensity of people doing work that matters, the countdown to Artemis III has already begun. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.